Okay. Some so this event code you might also have got through the mail. So you can use that event code that you have got through the mail. Okay. So I'm deleting this event code from here. So you might be you might have got this event code from your mail. So you have to use that event code. My voice is not clear. Can you please confirm?
There is some noise, sir.
Okay, just let me log into my. Let me use my mobile audio and join to another account and do that. It's good. Is it clear now? Hello?
We can hear you, but there is still some disturbance, sir.
Uh, I think there is issue with my laptop, but you can understand, right? Like,
Yes, sir, it's legible.
okay, fine, fine. So sorry. There is some technical issue at my end, but I don't have any options to resolve them. I tried to. Okay, fine. So we will continue with this. So fine. So you might have enrolled to this particular course using the code that you might have got through your mail, and you can see this particular screen with you. You just have to click on the fundamentals of accelerated computing with CUDA C++. Okay, so you click on this particular link. So can you please confirm is this particular course is opening? Okay, fine. So in this particular course, you have to select this accelerated application with CUDA C++. You click here and you will get the contents particular page getting loaded. You can see the start button here at the right side. You just click on the start button. You click on the start button and you will see this loading message here. Have you clicked on the start button? Can you please confirm? Here, the event code is there in the mail that you might have registered with. So please check your mail and you will have to and share the link of the and I know in the mail itself you might have got the URL to register for that course. So you just check your mail and if still you are facing any issues, please let me know. Okay. So are you able to see this particular launch button here? So Vipin, here is the URL to go to the page, and on this page you have to copy paste the event code that you might have received on your mail. Can you please confirm if you are able to see this launch button on your screen or still loading is coming? Okay, fine. So what you have to do is you have to click on the launch button. You just click on the launch button. So once you click on the launch button, the Jupyter notebook will open, and throughout this lab, we will be working on this Jupyter notebook. Okay, can you please confirm, is it open at your end? Okay, fine. Okay, so before moving ahead, I want to just confirm if anyone is still facing any issues to access the course. So we are mainly you just copy paste this link in your browser, this link, and the event code you have received on your mail. So you can use that event code and join the course. Is there anyone who is still facing the issues? The event code is there in your mail, so you can use that and open this link in your browser. So it will prompt for the event code. You copy paste that event code and then enroll the course. Once you enroll the course, you can see your name here. Then you click on the My Learning. Once you click on the My Learning, you can find the this particular course, that is Fundamentals of Accelerated Computing using C++. You click on that course, open this accelerated applications with CUDA C++ tab. Then click on the Start button. Once you click on the Start button, you will see this type of buttons here, Launch and Stop Task. You click on the Launch, you will find the Jupyter Notebook open on the another tab. So we are here as of now. If the code is not working for you, you can try to type it manually, because what happens is when you copy paste the code, some extra spaces will be. So try to type the code. Not fundamentals of deep learning, it's fundamentals of accelerated computing. Okay, let me check with the person who has shared this code, and I'll get back to you. Just wait for a moment. See, this code that is being shared by Priyanka, even though it's correct, but everyone should not use this code, because the code is mailed to you already. And I think the code, I'll share the code, just wait for a moment. Everyone don't have to use this code. This code This code is for half of the participants, and for remaining participants, yeah, I know, I know. So just wait, I'll update. I'll update the code. Just wait. Just wait, I'm sharing the code with you. Okay, you can, those who are facing the issues on the code received on the mail, you can use this particular code and enroll your course. Is my screen visible to everyone?
Yes, sir.
Okay, fine. I know those who are facing the issues, they'll do this code and enroll the course. Kindly let me know if anyone is still facing the issues. One more thing I want to update is that even though you will see this timer running out, but you can stop the task anytime and launch the lab again, and you will get this 3 hours again. So it's not that you will be getting only 3 hours to complete this course. So it's 3 hours for this particular instance. So moment you create the instance of the lab, you will get 3 hours to use that particular instance. Then once this limit is exhausted or you stop the task early, you can relaunch the lab and you will get another instance within 3 hours at home. So you can access this lab throughout the lifetime and 3 hours at a time. Okay. Suppose. Yeah, good. So once you will see this course, you just click on that particular course and select this first chapter, and then click on the start button. You will see these two buttons after some time. Then click on the launch. You will get this particular tab open. So this is the tab on which you will be working throughout this lab. Okay. So shall we move ahead? Or uh, those who are still facing issues, please let me know, because if you are not able to log in properly, you won't be able to get the certificate. So it's very crucial to get the course logged in, and so that we can do hands-on. So please let me know if anyone is facing issue. I'll wait for 2 seconds. Okay, fine. So no is facing issue now, and I hope everyone is having this tab open with you. Okay, so before moving ahead, let me just start with the introduction, why we are learning this particular course, and what is GPU basically. Okay, so I hope you all are familiar with the just wait. Okay, I hope you all are familiar with the C C++. So basically, those who know C or C++ coding, it is very easy to learn CUDA also. Okay, so one of the prerequisites is you should know the C++ basics. And not much, but at least you should know how to write program, how to create different functions, how to create variables, how to use them. Okay, so that much knowledge is enough. There is no requirement of any parallel computing knowledge. So directly uh, you can directly use this CUDA program to analyze your code. Okay, so no need of understanding the basic or you can say advanced concepts of parallel computing. So before moving on, we all know that GPUs are made in the market and widely used in gaming industry, on data center, on uh, everywhere, like audio parts also. So even in the medical industry also. So they are having huge scope, and nowadays AI is also on this. In the back of AI, there is a GPU. Okay, so there is an article in the Nature which says that the scientists in the University of New York have used the GPU-backed supercomputer to find the chemical structure of its capsid of the AIDS virus, and which is a perfect target for fighting infection. So this is all possible only because of the supercomputer which was backed by this Tesla platform with the 3000 Tesla accelerators, and all of these are GPUs. So if GPUs are not there, we might have made the CPUs, which is you can say we might have used the supercomputer, which is 5 times larger for the similar performance, and it would have taken a lot of time. Okay, so and many more like just now the COVID has gone, right? So for discovering the vaccines or to discover the different drugs also, we we have the systems which are backed by the GPUs. So we know that for the last 30 years, the Moore's law has stopped. As of now, the Moore's law has stopped. The reason is the number of the number of transistors in the CPUs are getting saturated. The reason is the size and the heat issue. So we have to go for the another hardware alternative, and that is a GPU, and which is started from 2010 onwards. So the saturation started from 2010, and this is the time from where the people have shifted towards using the GPUs for general purpose computing. Earlier, the use of GPU was only for the graphics applications within industries, but after 2010, the GPUs were used for the general purpose computations because of the power. So, uh, before moving ahead to the direct programming, we should know the fundamentals of what is GPU actually. we all know CPU, and we know the CPUs are optimized for single tasks, and they are having huge cache, right? And limited number of cores are there, limited numbers, but they are very powerful. As compared to that, the GPUs are having not many number of cores, but they are small in size, or you can say they are less powerful. And so the cache memory is very less in the GPU, and they are optimized for the parallel tasks. Okay, so this is the basic difference between CPU and GPU. So CPU is optimized for serial tasks, and GPU is optimized for parallel tasks. Am I audible? Hello?
Yes, sir. You are audible.
Okay, fine. So, coming back to the strengths of CPU and GPU, so basically CPU strength is that it has got very large main memory, very fast clock speed, latency is optimized, and the reason is because of the large caches. It has got a small number of threads which can run on very quickly. Also, the processors, or you can say the cores of CPUs are more powerful as compared to GPU cores. But the size, sorry, the quantity is more in case of GPUs. The weaknesses for the CPU is that relatively low memory bandwidth. So even though the cache memory is huge, but the bandwidth is less, cache miss is very costly. It has low performance per watt. So in short, it's not power efficient, you can say. So what happens here is if it is not power efficient, so if we go on adding more and more number of CPUs in our system, so more and more power is consumed. And if more power is consumed, the more heat is generated. So that is also one of the reasons why the people have shifted from CPU to GPU. The up to 2010, there was a there was a scope to increase the number of cores in the CPU because the size of the transistor was not much. But after 2010, or you can say 2010, the cores are basically the made up of transistors. So this CPU chip was not able to accommodate more number of cores because of the size of the transistor. So you can't have that particular compatibility, and also the heat issue was the another problem. Coming back to the GPU, it has high bandwidth, latency tolerant, and parallelism. So the GPUs are optimized for the parallel processing. So GPU is like the one who is very good at parallel processing but very bad at the serial processing. So when you try to execute any code on a GPU, you should execute only the parallel code and not the serial code. So we have two things here, CPU and GPU. CPU is good at serial codes and GPU is good at parallel code. So it has more compute resources. So here the green boxes you can see is you can visualize them as the cores, and a single core represents a compute resource. So the GPU has got more number of less powerful compute resources, whereas CPU has got less number of more powerful resources. Obviously, the GPUs have got the high throughput because it has capability to process more number of instructions at a time because of the huge number of cores. Okay, so it is power efficient, but whereas the weaknesses is it has low memory capacity because cache size is less. Whereas in CPU, cache size is huge. Also, per thread performance is low as compared to CPU because GPU cores are less powerful, whereas CPU cores are Coming to the real world application of CPU versus GPU, you can think of CPU as a like high write, super write, you can say, which can run, which can achieve the speed of up to 140 kilometer per hour. Whereas GPU, you can think of as a bus, which can accommodate more number of people at a time, but it has a speed limit of 80 kilometers per hour only. So it's on you to decide what you have to choose. Are you able, do you want to use two persons from from source to destination, or you want to do around 100 or 50 people from one source to another destination? So if you choose bike to travel for let us say 100 kilometers with the two people, so for two people, bike will be preferable. For 50 people, the bus will be preferable. I hope this makes sense. Is it clear up to now? Is it clear? Hello? Am I audible?
Yes, sir. Yes, sir.
Okay. And I will be real life real life example also works for you. Right? So you can think of CPU as a powerful small resource, right? So it can carry only two people with the high speed, whereas the bus can carry more number of people with the less speed. So it depends on the application, or you can say the data of the application, whether you choose less data or if you are having less amount of work to be done, you can choose go ahead with the CPU. But if you are having more amount of the work which can be parallelized, you can go ahead with the GPU. So the choice is yours. I'll skip this technical things. To respect these things. Now I'll present another presentation which introduces the CUDA basically. We all are we all are here that we all agree that what is the advantage of GPU over CPU, right? Up to now we have seen that. So let me now introduce you with the CUDA programming. So basically, what is CUDA that we are going to learn? So we will be exposing the GPU parallelism for general purpose computing. Why general purpose computing? Because GPUs were intended to be used for graphics oriented application, but as of now, the GPUs are being used in other applications also. So that's why we name general purpose computing system. Okay, so we will we will see how we can use the hello world, or we can print the hello world through the program. And we will start with the simple program, and then we will see how we can launch the CUDA C++ kernel. So basically, the function that is going to execute on the GPU in CUDA terminology, we call it as a kernel. Okay, so the function that is going to execute on the device. So GPU is known as the device in CUDA. Okay, so whatever the code that we are going to write to be executed on the GPU, we call it as a kernel. Okay, so we will see everything. So we all know that even some of the systems that we are having as of now are having the GPUs with them. Okay, so such systems we can call them as the heterogeneous systems. The reason why all them as heterogeneous is that they are having two devices. One is the CPU and another one is the GPU. They are different technologies. So normally the CPU we call as the host and the GPU we call as the device. Okay. Just give me a moment, I'm getting a call. Just hold. Hello, am I audible? Hello,
Yes, sir.
am I audible? Okay.
Yes.
Sorry, I just had to attend that one. Okay, so we have here that in our system we have CPU as well as GPU. Normally, any program uses CPU for execution of your code, but if you want to use a GPU, you need some special type of you can say syntax or code to be written to tell that okay, this code should be written on the GPU. Sorry, this code is to be executed on the GPU. So we instruct, or you can say we command the CPU that okay, this portion of the code it will execute it on the GPU. So GPU is like a passive person who is just waiting for the commands to be executed, which it is getting from the CPU. Okay, so here with the master is a CPU which commands or you can say which provides instructions to the GPU to be executed. GPU is very capable of executing more number of instructions at a time because of the more number of codes that it is having that we know already, right? So if you look, don't just let us say this is my portion of a code. Don't focus on the code. We are just we just partition this code into different sections. So let us say I am having a code and which is to be executed on a CPU as well as on the GPU. Okay, so what happens is the CPU first starts executing the code Here, this particular line indicates a thread. Okay, so you can say thread is a execution unit. Okay, so CPU is going to execute this particular serial code. Your code also contains some parallel portion. So here the call to the parallel function is happening, which is being defined here. Okay, in the same code. So you'll be writing a single code in which you are having a parallel function, a serial function, and a call to the parallel function, call to the serial function. Okay, so this, let us assume that this is my parallel function. This much is my parallel function. This much is my serial function. This is the call to the parallel function. This is the call to the serial function. So if I call the parallel function from here, the call will go here and it will be migrated to the GPU for execution. So now if you compare with the amount of computations that is being happening, you can simply see that more number of tasks are getting performed at a time as compared to CPU because GPU has got more number of cores. So if a particular thing is to be done parallelly, we shift that code, or you can say we instruct the GPU to process that particular set of code on it and return the result back to the CPU. So what GPU will do is it will perform some computation based on the logic and then return the result back to the CPU. Then CPU will work on that particular result, and if necessary, it can again call the GPU functions. So the code will go like this. The CPU will execute some part of the code, then call to the GPU, then again call back to the CPU, then again call to the GPU, and so on. So based on the need or logic of your application. So the basic processing flow is that you start with the CPU, the code when you start executing the code gets loaded into the CPU memory. I know this you all know that for execution of any application, that application need to be loaded into the CPU memory. I mean, this is going to your group, right? So when the application is there in a CPU memory and it gets the resources, it starts executing. The moment the program gets starts, you can say the moment program gets resources, it becomes a process, right? And in terms of, you can say, unit of execution is a thread here. So a thread gets executed on a CPU, and the moment it encounters the call to the GPU function, we call it as a kernel. What it does is it first copies data from CPU memory to the GPU memory because we all know the data is there in a CPU memory because the process is executing, right? But the CPU is unaware of that. So first we need to migrate the data from CPU to GPU because everything that we are going to from the data, from the computation is going to be done is on the data. So the data is to be shifted from CPU memory to the GPU memory. This is the first step. Then we load the GPU program to execute. So we call the GPU function. We call it as a kernel launch. Okay. So in terms of CUDA, we call it as a kernel launch. So we launch the kernel and perform the tasks based on the logic. Once we perform the task, we get the result. We copy back the result from GPU to CPU. So this is the basic flow of any CUDA program that we are going to write. Okay. So now coming back to the program. So can you tell, is this clear as of now or any doubt? Please let me know in the chat. Are you all with me? Hello? Is it clear? Okay. So shall we move ahead to the program now? Please interrupt me if you are not getting anything. Okay. So I'm there to help you. Please let me know if you are facing any difficulty in getting the things. Okay, fine. So we all know this is a simple C program to create the hello world. But the thing is, this particular message is being displayed on the on our screen, and this program is processed on the CPU, not on the GPU. So this is the CPU function which is being executed on a CPU. Now, it is to be noted that any C program or C++ program can be compiled and can be compiled with the help of any other compiler also. So that is the compiler for compiling the CUDA programs. But any CUDA program is basically a C or C++ program, right? So NVIDIA compiler, that is NVCC, can understand the C program. So even though you have not written any parallel code, you may do any, you can say kernel here, which is to be executed on the CPU, but still you can compile the code with the help of the CUDA compiler. You can say NVIDIA compiler. The compiler name is NVCC. Okay, so but the thing is, you have to save this file with the extension .c. Okay, so even though this is the code meant to be executed on a CPU, you can save this code as, you can say, the name of the file .cu. So if you save this file, then extension cu, it becomes a CUDA code. Even though it is not going to be executed on a GPU, but still if you use this extension, your code will become a CUDA code. Now, once it is CUDA code, you can compile this code on the NVCC compiler, or you can say NVIDIA compiler. So, this code is going to be executed on a CPU because we are not calling the GPU. Okay, we are not writing any GPU function here. So, it runs on the host. So, the host means a CPU. Okay, so NVIDIA compiler can be used to compile the program with no device code. Device means GPU, right? So if you compile and execute this code, you will still get the result. Okay. Now let us move ahead with the first version of GPU code, or I can say device code. Are you all with me? Are you all with me? Please reply. Hello. Okay. Fine. Fine. So, if you look at the definition of my kernel, so my kernel is the name of the function, void is the return type. Okay. One more thing is the GPU kernel that is going to be launched from the CPU has a return type of void. Okay, so it does not return anything. But still, if it produces the results, you have to copy the data. Okay, even though it does not return, but you can copy the data back to the CPU from the GPU. Okay, so it is very important to note that any GPU kernel which is getting launched from the CPU has got the void as the return type. Also, one more thing is to be noted is this is the new thing, right? So double underscore global double underscore. So this is a double underscore, right? Underscore global underscore. So this is how you tell the CPU that this particular code is meant to be executed on a device side, or you can say on the GPU side. Okay, so this global keyword tells the CPU that this is the device version of the code. As of now, nothing is written. Okay. One more thing is we all know that we can pass the parameters here, right? As of now, there is no parameter, but you can pass as many parameters as you can. So these parameters we pass from the CPU call. I get that to here, but just for your information, I'm doing any device kernel should have global the underscore underscore global underscore underscore then void. Okay, so this is how you start writing your kernel. And then you can write anything as you wish in your kernel. Then any parameters if it is accepting, any inputs to your kernel that are coming from the CPU, any data that is coming from the CPU, you write it. And as of now, it is doing nothing. No code is written, but normally you will write the kind of code, you can say the version of the code that is to be executed on the GPU. So in this case, nothing is written. So nothing will be executed on the GPU, but still the call to the GPU will go. Okay, so now coming back to the CPU code, so this end node, so this is the CPU function, or you can say the main function. So in the main function, this is the call to the kernel. So normally we know how we call the function in C. We call the function in C by simply writing the function name uh, and the and the round brackets, right? So here the new thing that you can observe is the triple angle brackets, opening and closing, and one. So this is the launching parameters. So this one is the launching parameter. This we will learn what are these things in detail. Okay, so but as of now, just think of it as the launching parameter. So this is how the GPU function will be called. Okay, normally it is the CPU function. You don't have to use this, right? You simply say my kernel and then this open and close round bracket. But because you are calling the GPU, you call it with the help of the launching parameters. So this printf hello world is going to be executed at the CPU end. Okay, so there are two different elements, or you can say two different syntax we have seen. One thing is the GPU core or GPU kernel that we have discussed. So this keyword global indicates the function that it will run on the device. It is called from the host code. So this global indicates that it is going to be executed on the GPU and also is going to be called from the CPU. Okay, so this because of this keyword, the NVCC, the CUDA compiler is able to separate the source code into two parts. One part is going to be executed on the host side, and another part is going to be executed at the device side. So the device function is processed by the NVIDIA compiler, and the host function is processed by the standard host compiler, that is GCC or CWXC. Now, coming to the launching parameters, you can see the triple angle brackets from after the name of the, or you can say call of the function. Okay, so this is nothing but the kernel launch. So we are calling the GPU function. So CPU function is called normally, but GPU function is there is a special syntax to call the GPU function, and this is the launching parameter. So that's all. So this is how we launch the CUDA program. Okay. So fine. So this was all the introduction about what basically is the GPU and how to write. You can say how to start with writing the CUDA syntax. So now everyone can see this Jupyter notebook I hope. Okay, so we will directly jump to the lab question now. So everyone is requested to open this Jupyter notebook. Everyone is here? Hello? Anyone is here? Okay, fine. So, before going ahead, shall we take a small break of 10 minutes? Shall we take small break of 10 minutes? Then we will directly start the lab. Okay, so we will start. Okay, so I will request everyone to just stop the instance at your to launch the instance if you have stopped it earlier. We will launch this instance and follow the instruction that I'm going to tell. Okay, so in the first session we have just seen the introduction to CUDA and what is GPU architecture that we have seen and why GPUs are being used. So we are now ready to use this heterogeneous or we can say accelerated systems in our lab. Okay, so before moving ahead, let me first tell that there is a command to let us know that what type of GPU that we are having in our system or in our lab. Uh, so the command is NVIDIA-SMF. So this command will work only if you are having the GPU installed and the driver installed in the system. So the lab that we are is already capable, or you can say is already there for this lab, and GPU is already installed. So this command will work. So to execute this command, uh, in the first cell, you have to click on this particular text field and then shift enter. So press shift and enter from your keyboard on this cell. So you have to press shift enter both at a time. So are you able to see something, output something like this in your browser? Can you just reply? So in your notebook, you have to select this cell and press shift enter. You will see this type of output. So can you please confirm? Okay. So two people have confirmed. So we'll go ahead. So this is basically to confirm whether we are having the CUDA and GPU installed in our system that we are going to work. And this type of output tells us what is the driver version, what is the CUDA version, and what type of GPU that we are having in our lab. So you can study this later on, but this simply tells us that okay, we are up and ready to use the GPU for our programs. Okay, so first let me so everyone please come back to the Webex screen and I'm going to show you the another presentation. So I think you are also able to see this particular cell, and later on after this course you can access this presentation again by pressing Shift and Enter, you will see this particular slides in your browser itself. So you can click on the Start slideshow and you can see the slides. So that is for the data one. But please come back to the WebEx screen and then I'm going to share. Okay. So come back to the WebEx. So this we have seen very briefly that CPU versus GPU. So how CPUs work and how GPUs work. So in CPU, the data is allocated on the CPU that you have seen. So what happens is we initialize the data onto the CPU. Then what happens is the CPU will perform the work on this particular data, and for after verification we get the result. Okay, but this is not the case with the heterogeneous systems, or you can say the accelerated applications. So what happens in the accelerated applications is we have data with us. So that data is to be allocated onto the host or a device based on the requirement. Okay, so and that allocation in CUDA. Okay, I'm talking about the CUDA. So this is the function in CUDA which is used to allocate the memory for that particular data in the unified memory. So unified memory is a terminology which is being used in CUDA to tell that this particular data is going to be accessed by host as well as device. Okay, so once you initialize the data, or you can say allocate the data with the help of this function that is CUDA envelope managed, the data that you are going to use, or you can say this data is going to be accessible from CPU as well as GPU. So earlier, what might used to happen is for dynamic allocation, you might have used CLOC or MLOC for data allocation, right? So in CUDA, we use CUDA envelope manage. So this function, the data allocated with this function is accessible from CPU as well as GPU. Okay, so this is the first step. So you initialize the data. Okay, so then once you initialize the data, you can perform the work, and let us assume that the work can be done parallelly. So we want to work on the GPU. So this work is being performed on the GPU. So if you look at the difference between the two diagrams, you can see the CPU perform work is getting this much amount of, let us say we are having 1, 2, 3, 4, 5, 6, 7, 8 unit of work to be performed. So let us say 1 unit is taking 1 unit of time to get executed. So it is taking around 8 units of time to be performed, because CPU is going to be, or the CPU is going to active sequentially. We are not having enough compute resources to parallelize. But same data, let us say it can be parallelized, and we are having, let us say, 4 cores, and sorry, 8 cores, and we are allocated it in such a way that 4 works is getting works. Can say they are divided into 2 sections. So only 2 units of time is required. So we are working parallelly. So one more thing is that when the GPU is performing, because they are 2 different devices, CPU can also work. So CPU and GPU can work together. So it is not that when GPU is working, CPU will sit together. No. When GPU is working, CPU can also work on another part of the program. Okay, so CPU and GPU can progress together. Okay, so therefore it is mentioned that the work on the GPU is asynchronous. It is not synchronous, right? So if it is synchronous, then CPU would have waited for GPU to complete its task. But in this case, GPU is asynchronous. Therefore, CPU and GPU can work together. They won't depend on each other. So what will happen if GPU work and CPU work need to be synchronized? So let us say the result from GPU. On that result, I want to work in the CPU. So for that, I need to make the CPU wait until GPU completes its task. Okay, so for that purpose, we need extra syntax or we can say extra statement to be inserted so that both CPU and GPU are synchronized. Okay, so that point we have to identify in our program that okay, this is the point where I need the GPU to be both CPU and GPU need to be synchronized here. That means what? CPU and GPU should wait for each other. Even though CPU is finished first, it will wait for the GPU to finish. Or if GPU is finished, it will wait for the CPU to finish. So here is a line wherein we are adding the discipline in one kind of table. This is the point where you both have to wait for each other. Okay, and this is being introduced with the help of CUDA device synchronize. So CPU code can sync with the asynchronous GPU work, waiting for it to complete. Okay, with the help of CUDA device synchronize. So I hope everyone is clear that first we need to allocate the data to be used by both CPU as well as GPU, and this is being done with the help of CUDA time block language. Once the data is being allocated, I can work on the data with the help of CUDA kernel. We will have to launch the CUDA kernel, right? With the help of triple angular bracket. So that we will see soon. Once the work is done, we have to write the CUDA device synchronize statement to make sure that both the asynchronous GPU is synchronized with the CPU work. And after that, we can perform the verification whether the computation is correct. So if the verification is correct, we can publish the result. Okay, so is it clear up to now? Any problem? Any question? Any question? Please let me know. Any question? Are you ready? Is it easy going? Hello? Please reply. Am I audible?
Yes, sir.
Okay. Fine. So, is it okay? Like, you are not getting right? Or any difficulty in understanding? Are you able to understand? Okay, fine. Thank you. Fine. So now we are equipped with the sufficient knowledge to write our first CUDA kernel. Okay, you all will be working with me. Okay, so we will also understand clearly. So this is very clear that CUDA code is written and the file is saved with the .co extension. So the .co tells that this is a CUDA file and is compiled with the NVCC, right? So that is the NVIDIA compiler. So before starting the, or you can say before learning the GPU version of a function, let us see how the CPU function looks like. So if you look at this is the CPU function normal CPU function which is getting invoked from here, right? The highlighted part. So if you look at the main, so if you compile this code, so the serial version will be compiled with the GCC, and the normal in the parallel version, you can say this part will be compiled with the window NVCC. The two parts will be divided. One is the CPU part, and another one is the GPU part, or we can say host code and device code. So two functions are there. The CPU function is a host function, whereas the GPU function is the device function. So you can clearly see the difference between the definition of these two functions, right? CPU function we all know how to write. GPU function we just learned that GPU function will start with the input underscore underscore global underscore to write, and then the name of the GPU function. As of now, there is no parameter, but you can have the parameters if you wish to. It is not doing anything, it is simply printing this message. We are not computing anything, right? We are just showing the message. Okay, so as of now, no computation is happening. This line is going to call the CPU version of this function, that is CPU function. The call to the GPU is made with the help of launching parameters. So this we have seen in the previous, before break, right? That you write the name of the GPU function, then triple angular bracket. This one we will see soon. Okay. So as of now, we just think of them as the launching parameters. So these are the launching parameters for us. Okay. So and then this open and close bracket. So inside this, you can pass the parameters, or you can say pass the input to the GPU from here. So this will be taken care by this. I hope you know this, right? So this is where you call the GPU function. And as we have seen, this CUDA device synchronize. What is the use of this? Can anyone unmute and tell? CUDA device synchronize. What is the use of this function? Can anyone tell? Why there is need of this line? Can anyone tell? Good. Wait for GPU response, or you can say simply to synchronize the asynchronous GPU curve. Okay, or you can say your CPU is going to wait until the GPU is finished. So you are making sure that the asynchronous function is synchronized at that particular point of code. Okay, so here what happens sometimes is the CPU will launch the GPU kernel, and then it will go ahead with the code, and there is nothing. So it won't print anything because GPU is yet to be executed. So it will take some amount of time to launch the CUDA kernel, and that is the overhead. So CPU will simply launch, or you can say, give instruction to the GPU that okay, look, this is the function we have to work on, and then it will continue. So if there is no CUDA device synchronized, your GPU function won't be able to, you can say, print the result onto the screen. That's what we are doing here, right? So the CPU will terminate, or you can say, obviously your program is getting executed on a CPU first, and then you are launching the CUDA kernel. So it won't wait for the CUDA kernel to get executed and will terminate the program. That's why we need this CUDA device synchronized. So everyone, please go back to the this notebook. You will see this explanation. Okay, this explanation we already have covered in our presentation. Only the thing that is to be covered is this launching parameter. Okay, so to repeat again, this global keyword indicates that this function is going to be executed onto the kernel side and is going to be launched, or you can say called, at the CPU side. So now if you look at the launching of the GPU, so this is the line which is going to call the GPU kernel. Okay, so this is the GPU function and these are the launching parameters. So when you call the GPU, we call this function as a kernel. Okay, in the GPU function you normally call as a kernel, and this line is nothing but the launching parameter. So these are the launching parameters. This one dash one are the launching parameters. So hello, any question? I think someone is. Can you mute yourself? Hello, am I audible clearly?
Yes, sir.
So these are launching parameters. We also call them as the execution configuration. And
GPU.
hello.
Sir, I can mute them, but then you'll have to unmute yourself again.
Is there any question from the audience? Okay. So if you look at this parameter 1, so this is going to launch the one block of thread, and per block there is one thread. So this first parameter is the number of blocks. The second parameter is the number of threads. So now just don't bother about what is block and what is thread that we are going to see in the thread hierarchy. But as of now, we just think about that. This is nothing but these two are going to be multiplied to get the total number of threads that are going to be launched. So this first parameter into second parameter is the total number of threads that we are going to launch. So as of now, only a single thread is going to be launched, right? So at the high level, the execution configuration will allow us to get, or you can say, to define the thread hierarchy. Okay, so in this thread hierarchy, you can think of the threads are the execution limit. So anything that you want to execute on the GPU is going to be executed with the help of thread, right? So if I want to work on a particular piece of code or piece of data, I need a thread. So how to create a thread? So thread is getting created with the help of this launching parameters. So that's what you can think of, right? So this launching parameter, or you can say this launching configuration, is creating, or you can say is going to give me the set of threads that I'm going to work on. Okay, so how many threads? So the number of threads we can get it with the help of simply multiplying these two parameters. The first parameter is the number of blocks. The second parameter is number of threads in a block. So if you think of now, let us say that this is my GPU device. Okay, let us assume that this is my GPU device. In this GPU device, I need the thread to perform the work. Okay, but threads are not directly launched. I am going to launch the threads with the help of thread hierarchy. So the threads are getting launched with in build. Okay, so in build there is block, and in block there is a thread. So if you think of this as a grid, the grid consists of multiple blocks. Okay, so here is let me just let me show you the presentation directly. So we will. I hope you are following me. So let us come back to the launching parameters. Okay, so can anyone tell me what this perform work is? Can anyone tell what this perform work is? So what is this? Can anyone tell what is this? Perform work, triple angular bracket 2, 4, triple angular bracket close, and this parenthesis and this bracket. Can anyone tell what is this? Good. So this is the GPU function call. Okay. So this is the GPU function call from the host, or you can say from the CPU. Okay. So this is where we are. So we are at the perform work stage. So this perform work is getting called from the CPU side with the help of this statement. Okay. So can you guess how many threads are launched? How many threads are launched? The first parameter into second parameter. So total is 8. So in total 8 threads are launched. So if you look at this white rectangles, these white rectangles represent the threads, right? So how many white rectangles are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 threads are there. Now, in this launching parameter, what I am saying is this first parameter indicates the number of blocks. So total 8 threads are launched. But how they are launched? They are launched in block of 2. And in each block, the same number of threads are there. So 4 threads are there. So this 2 indicates this blue box. Okay. So this blue box is a block. So how many blue boxes are there? There are 2 blue boxes. So 2 blocks are there. This which indicates this first parameters. 4 indicates number of threads in each block. So therefore 4 threads in this block, 4 threads in this block. Okay, so basically GPU and this black box is nothing but a grid. Okay, so if you look at if you visualize, if you can visualize, you can think of it as a grid of block of threads, right? So this is a grid of block, or it will be grid of blocks of threads. So in a grid there are multiple blocks, and in each block there are same number of threads. So it won't be the case that one block is having 2 threads, another block is having 4 threads, another block is having 5 threads. No. If you are writing a kernel launch parameters, the second parameter indicates the amount of threads that are going to be there in each block. The first parameter indicates the number of blocks that are there in a grid. So this black box is a grid, blue box is a block, and white box is a thread. So this is a thread hierarchy. Okay, so this we have already discussed that GPU work is going to be done in a thread. So we need a thread. So how the threads are created? You create them with the help of this launching parameter. Okay, so each thread is created. So many threads run in parallel. Okay, so in a block, in 2 different blocks, they are running in a parallel fashion. Okay, now this collection of threads is called as the block. Okay, so this collection of 4 threads is a block, collection of this another thread, 4 threads is another block. So this block is independent of this block. Okay, so there are 2 blocks. In each block, there is a collection of threads, equal number of threads, equal number of threads. So each block is having same number of threads. Okay, there are many blocks in a grid. So you can have as many blocks as you wish to, as per your requirement, or you can say as per the data that you are going to work on. Okay, so this application seems to be very small application, therefore they are launching only 8 threads. But if you wish, you can launch as many threads as per the requirement. The collection of blocks is called as a grid. So normally, when you launch this kernel with this parameter, you are basically launching the grid of thread, the grid of blocks of the threads. So at the very top level, there is a grid. After grid, in the grid there are blocks, and in the blocks there are threads, right? So the collection of blocks is grid. So we all now know that collection of threads is blocks and collection of blocks is grid. The GPU function that is perform work is known as the kernel, right? So this perform work is a kernel. These are written, the things that are written in the triple angular brackets are known as the execution configuration, or you can say launching parameters. So with this launching configuration, we launch the kernel from the CPU side. Okay. Now this execution configuration defines the number of blocks in the grid. So this highlighted to this green tool indicates two green blocks, right? This indicates number of blocks. The second parameter indicates number of threads in each block. In each block, 4 threads are there. So every block in a grid contains the same number of threads. This also we will discuss, right? So this is the thread hierarchy. I hope everyone is clear now. Everyone is clear with this kernel launch statement. Any questions so far? Any questions so far? Any question? Okay, fine. So this also we have seen why this CUDA device improvement is required. Now everyone is requested to click on this particular link here. You can see 01 hello gpu.cu. So you click on this particular link. It contains what it contains. It is this file you have to work on. Okay. So please don't do anything as of now. You just open this code. Okay. Now in this code, you can see there is a hello CPU and hello GPU. Two codes are there. Okay. So what I have to do is I want to make this hello GPU code as a device code. So what needs to be done here? Can anyone tell? If I want to make it as a kernel, what needs to be done? Can anyone tell? What needs to be done?
Underscore
What is very good. So here I need to have this underscore without any space global again underscore with one space. Okay. So this keyword makes sure that this is the kernel. Okay. So this one thing you have to do. Another thing. Now this hello CPU is going to give a call to this CPU function. This is very perfectly okay, right? But now, can you refactor this call so that you launch this particular kernel? So what is required? Can you tell me? What is required? I need launching configuration, right? So for that, I need triple angular bracket. If let us say I want to launch one block of thread and one thread per block, I will put 1, with closing angular brackets. So this is my kernel launch, right? One more thing that is to be done here is what is to be done now? Can you hear me? For synchronization, I need to add what I need to add? CUDA device. CUDA device synchronize. Once this is done, so only few modifications I have added. What are they? I have added this global keyword here. Then I have changed the point to the GPU to make it a kernel launch. Then I have made the CPU to wait for GPU to perform its task here. So here I am synchronizing. Here I have made the synchronization statement. Anyone modified their code like this? Anyone is done? Can anyone tell? So have you modified this code at your end? Hello? I assume that you have made these changes. You have to save this file and then control S, you save this file, then come back to the notebook here, okay, and then you click this cell and press Shift Enter. Once you okay, there is one mistake. Once you compile this code, okay. Yeah, no, just wait. You have to modify this line here. Instead of CPU, you write here GPU because this there is a typing mistake there. So you just modify this as a GPU. So because it is going to be executed at the GPU and want to make sure that okay, ultimately this function is getting called. So once you execute this, you will see this output. Hello from CPU, hello also from the GPU. Can anyone confirm have you executed this code? I hope all are with me. Okay, fine. Good. So now there is a time to experiment on this line, on this code. So what I would suggest is you first remove this underscore global from this code and try to re-execute the code again and see what happens. So remove this global keyword and try to re-execute the code. What will happen? So you will see this error. What error it is saying? The first function call cannot be configured. So what does it mean? So it is assuming that it is going here. It is assuming that there is a CUDA function call, but when it comes here, it does not find any global function here. So that means what the compiler will shout on us that okay, do not launch the CUDA kernel which is not yet defined. So this CUDA kernel launch is not configured properly, or you can see you are not launching it properly. Okay, so just do this global again here. Okay, now let us say, let us try to remove this CUDA device. I will simply comment it. Okay, you can also comment this line CUDA device implement. Let us say that we have forgot to add this line. What will happen? Then any guesses what will happen? What will be the output after commenting this line? Any guesses? What will be the output if I comment this? Will the code compile? First question, will the code compile? Yes or no? Okay, it will compile. What will happen? Will it execute? Will it execute? Yes, it will execute. But the problem is it won't display the result from the GPU side. The reason is CPU is not waiting for the GPU to publish the results. right? So let us rerun this code. If you look at, even though we have called the GPU properly, the code is compiled, and we are calling from here, but still the output from the GPU is missing. The reason is CPU is not waiting for the GPU to complete the task. It is just launching and just going ahead, and there is nothing to execute for the CPU. So program will terminate. So we don't see any output from the GPU. So that's the reason we need to put this CUDA device synchronize statement here, so that our CPU is going to work for this kernel to get finished. Okay, so now remove this comment and recompile the code again. You will see the message from the GPU again. Okay, so there are more things that you can explore later on in this the same notebook. It is available to you for lifetime now. So you can explore the different things. Okay, so we will move on there because of the time limit. Everyone is clear? Any questions so far? Any questions? Any questions? Okay, fine. Fine, fine. Thank you. So if you look at the command to compile and run, you will see this line. So for us, NBCC is the compiler, or you can say invocation to the CUDA compiler. This minus arc equal to SM70 is the architecture that we are going to compile our code for. So don't know technicalities, you just assume that this is the architecture we are focusing on. So even if you remove this particular option, your code will compile. Okay, minus 4 is nothing but the object file that we are going to create, the name of the object file. So in this case, whatever written after minus 4 is going to be the object file. So this out is the object file that we are going to create. Sum CUDA.c is the name of the function that we are writing. Okay, and minus run tells that you compile and run in a single code. Otherwise, what will happen is once you compile this code, it won't run automatically. You have to specify /out. Okay, so therefore, to make sure that your code is going to be executed the moment you compile, so that is the minus run option. So you can compile and execute the code without these two options also. But to make sure that code is executed at the same time the compilation is successful, this minus run option is there. Okay. Any question here? So this is the command to run your CUDA program after compilation. Okay, so CUDA thread hierarchy we have already covered. So now it's time to play with this. Let us try to launch this CUDA command and launching parameters. Okay, so earlier we have launched the CUDA kernel with the single thread. Now let us say I want to launch many number of threads. So we already know that the first parameter is the number of blocks, the second parameter is the number of threads per block. Okay, so now we can specify the number of different number of blocks and number of threads per blocks, and try to launch the kernel again. Okay, so let us try to click on this link, okay, and again we have to refactor this particular code. So we all know that we need to insert the global unique keyword here. Okay. So this makes this first parallel function as a CUDA kernel. Okay. Now here I want to make this as a CUDA launch. Okay. So first let us say I am launching this kernel with the single thread. Okay. Here I have to introduce CUDA device synchronize. This is similar to the previous code that we have seen, right? So it will run. So if I so this should be running in parallel. So this code is executed, but it does not. You can say visualize the number of threads. We can't say how many threads are on. Is executed on a GPU. So for that, let us launch different number of threads. Okay, so let us say I want to launch the threads in full blocks and 4 threads per block. Can you guess how many times this should be running in parallel will be printed? How many times it will be printed? Can you tell me? Total 8 times, right? Because each thread will execute this kernel. So this kernel is nothing but the piece of code given to a single thread. So whatever you want to perform for a so whatever you want to perform for a single thread, you write it in a kernel. So the code that you are going to write in a kernel is going to be executed by each thread in a block. Okay, so there are 8 threads. So 8 threads will print this message. Okay, so let us see if really execute. So if you look at, you can see the 8 statements getting executed. Okay, you can also go back and try to reconfigure the kernel launch here in this code. And let us try to follow these particular questions that they are asking. So what they have asked is, you launch and you execute it on the 5 threads or executing in a thread block. So we need to create a single block, and in a single block, I want to launch 5 threads. So can you tell me what is the launching parameter that I should be having? So I need one block, and in that block, I want to launch 5 threads. So what should be the launching parameter? Very good. So I should be using 1 comma 5, right? So 1 comma 5. So this is the launching parameter. So let us try to see whether 5 threads are launched. So see, there are 5 threads getting launched. Okay. Next, what they are asking is, you execute inside 5 thread blocks, each containing 5 threads. So can you guess how many times this should be running in parallel will be printed? Total 5 blocks, and each block contains 5 threads. So how many threads I am launching? 5 into 5 that is 25. So 25 times this code, this message will be displayed. So let us say again I am launching 5 blocks, and each block is having 5 threads. So let us run this code. So if you count, it will come out as 25. Are you getting? Any questions so far? Any questions so far? Any question? So it said, but it played only one time. Okay, so can you just compare your code with this? Can you unmute yourself? Can you unmute yourself, Priyanka? Priyanka? Hello?
Yes, sir. Yes, sir.
Okay, so have you changed the seventh line to underscore underscore global underscore underscore global?
Yes,
Okay,
sir.
it is printing that means yeah, there is problem with the launching parameter, right? So first of all, are you accessing this same file 01 underscore first underscore parallel dot c?
Yes, sir. Yes, sir. For solution.
Yeah. So 19th number line, you have to change the launching parameter to let us say 1 comma 5 or 5 comma 5. Have you changed this?
Yes, sir.
What is the launching parameter that you have put?
5, 5.
5 5. Okay. And then have you written this CUDA device synchronize?
Yes, sir. I didn't. I put my code at chat.
Okay, let me see. Okay. So basically this should be executing. Why it is not executing? It should be executing. Let me copy paste your code in my is there anyone who is facing the issue? Okay. So if I yeah, I should execute
Sir,
it.
sir, maybe I put the space between 5 and 5.
Yeah, just change that and check.
Okay, okay, sir. Thank you.
Done?
Yeah, sir. Definitely.
Yeah, fine, fine. So see, if you are going to launch, you launch it properly because it is executing that means there is problem in the launching parameters, right? I hope other people are able to execute. Everyone executed this code. I assume everyone have executed. Okay. Now, see, we have launched many number of blocks and many number of threads per blocks. Now it is right time that each thread will do what work. We can see which thread will access what data. So for that we need indexing, right? And for indexing, there is a special variables, or we can say special CUDA syntax to get the uh, index of a particular thread. That okay, this is my thread ID, and this thread ID is unique for me. So in CUDA, uh, we have different variables to specify the thread index, and there is some formula with to which you can tell that this is the unique thread index in my kernel branch. Okay, so we will see that presentation. Everyone is requested to come back to the WebEx and look at this presentation. I hope everyone is familiar with the arrays. So as there is array indexing, we can think of this kernel launch as group of threads getting launched, and they are launched in grid in blocks, and every block contains threads. Okay, so there should be a mechanism to, you can say, to correctly identify what is the global thread ID, or you can say what is the unique thread ID that I'm working, that I'm doing. Okay, so we know that inside kernel definition, we have this launching parameter. This launching parameter, we will think of 2 and 4. So 2 means 2 blocks, 4 means 4 threads per block. So in a grid, there are 2 blocks, and in each block there are 4 threads. So let us say I want to uniquely identify each thread uniquely. Okay, I want to identify each thread uniquely. So there is a mechanism, and there are CUDA provided variables which describe the ID of current executing thread, ID of current block, and unveil. Okay, so first of all, we know in a thread hierarchy that there are, as per this kernel launch, there are 2 blocks in this particular thread. Is it or not? So this first parameter is the number of blocks, which also specifies the grid dimension. So what is the grid dimension? Grid dimension is 2 here, right? So there are 2 blocks, therefore the grid dimension is 3. And this grid dimension is identical X. So this is the way you get the grid dimension. There should not be any spaces or any spelling mistakes in writing this particular number. Okay, so grid dim.x is the number of blocks in the grid. In this case, it is 2. Okay. Now, next is I want to identify which block my thread is in. So that you can get with the help of block idx.x. So let us say currently I am working on this particular thread. So on this thread, if I want to know which block this thread is in, so that you can get with the help of block idx.x. So it will return 0. In C, in CUDA, the block IDs will start from 0 onwards. So if there are 2 blocks, each block will get unique ID. The first block will get 0, the second block will get 1. So this block is having 0 as block ID. This block is having 1 as the block ID. Okay? Inside each block, each thread has got their own ID. So this threads. So how many threads are there? So total 4 threads are there, right? So this 4 is nothing but the number of threads per block. So number of threads per block is also known as the grid dimension. Sorry, block dimension, right? So what is the block dimension here? Block dimension is 4. And that we can get with the help of the variable block dim.x. Okay, so this block dim.x will give you 4. The grid dim.x will give you 2. Is it or not? The block idx.x will give you 2 different things, either 0 or 1, based on the thread that you are working. If you are working on this thread, the block id.x will return you 1. If you are working on this thread, the block idx.x will return you 0. One more thing is, all the threads in the same block have same block ID. All the threads in this block have the same block ID. So in a block, all the threads have same block ID. Is it clear to everyone? Is it clear? and block bin.x will return me the total number of threads per block. So in this case is 4. And we know that all blocks in thread contain the same number of threads. Inside the block, we are having threads, and each thread is identified uniquely inside the block with the help of thread ID x.x variable. So this thread ID x.x will return me the unique thread ID for that particular block. I'm saying for that particular block, not in the middle. So you can see this 0 as this thread ID, and again this thread has also got 0 as a thread ID. So if you are trying to access, or you can say if you are trying to uniquely identify a thread having multiple blocks, only thread ID x.x won't give you a unique thread. The reason is thread ID x.x is same for two different threads in two different blocks, but is unique in a single block. Is it clear, Sabina? Is this clear to everyone? Any questions so far? Any question? Any questions? Okay, let's repeat once. Okay, so what you want? This thread ID x dot x. Deepak, can you please unmute? Can you please unmute? Hello? Hello? Deepak? Okay, let me, I hope after this everyone is clear that blocks in grid have same number of threads. So this block and this block, these are two different blocks, and each block is launched with the same number of threads. In this case, 4. So this block dimension is 4, this block dimension is also 4. So obviously blocking.x will return me the unique value, right? So blocking.x will return the same value for all the threads in my kernel launch. So if I call blocking.x, everyone will return me 4. But here the problem is thread ID x.x, because thread ID x.x is going to give me the thread ID within a block. Within a block, and say. So if there are two blocks, this thread ID.x will give me the thread ID within the block. Unique thread ID within this block. So if there are 4 threads in the block, I am getting 0 to 3. 0, 1, 2, 3. Again, 0, 1, 2, 3. So thread ID x.x is going to give me the thread ID unique to the particular block. So this block is having thread with ID 0. This block is also having thread with ID 0. Are you getting my point? So thread ID x.x, if I call it on this thread ID x.x, can you tell what it will return? It will return 1. Again, if I call thread ID x.x on this thread, what it will return? It will also return 1. What is different in the block? Are you getting? So in this case, the thread ID x.x is 1. In this case, it is 2. In this case, it is 3. Again, in this case, it is 0, 1, 2, and 3. I hope it is clear to you now, Deepak. Is it clear now, Deepak? Hello? Anyone has any doubt? So shall we move ahead? Shall we move ahead? Any questions so far? I am just spending more time here because this is the very basic thing, and if you don't get it, you won't get anything. So that's why please pay attention, and if you have any simple doubt also, please be free to ask. Okay? I'm going to help. Fine. Now, the problem here is even though we have got grid of lot of threads, but we are still struggling to find the unique thread ID because even though I'm having thread ID x.x, but it is going to give me the unique thread number within a block only, not within a grid. So I should compute the global thread ID. So if this is the thread that I'm working on, I should know its unique thread number within a thread. I can get its unique thread number within a block, but within a thread, I have to calculate. There is no, you can say, a variable provided for having the global thread ID. So that we have to compute on your own. Okay? So that's what we will see. So again, go back to your notebook and you click on this 01 thread and block idx.cu file. Okay, don't click on the solution. It will directly give you the solution. So you click here, we will modify this. Okay, so this file contains the working kernel which is printing a failure message. Okay, and what you have to do is you have to open this file and update the execution configuration so that the success message will be printed, and just try to do this. So what is missing here? Can you tell me what is the problem in this logic? Just focus on this launching configuration. Okay. What is the launching configuration? 1 means how many threads are launched? How many threads are launched? In this launching configuration, how many threads are launched? 1, right? But in my kernel code, so obviously this is a kernel code, right? Because the underscore global underscore global void is written. That means this is a kernel. So from this, I'm going to launch the kernel. After the kernel is launched, the kernel is launched with 1 thread, and inside this kernel launch, what I am trying to do here in a if statement. Thread ID and dot x equal to 1023 means what? I am going to print this success message only if I am in a block with ID 255, and within that 255 ID block, I am the 1023 ID thread. So if that is a thread that is going to execute this kernel, then and then only you print the success message. Otherwise, you print the failure message. Are you getting my point? So, yeah, what we are doing here, we are checking what is the thread ID. Thread ID x.x is going to be the thread ID of my thread. Block ID x.x is going to return the block ID of my thread. So if I am launching the thread with 1 block and a single thread per block, what is thread ID x.x then? 0. What is the block ID x.x? 0. So both the things are 0 and 0. Okay. So I'm not having a thread in my kernel launch having this condition satisfied. So therefore, my thread will execute this else part. So let us try to execute this line first. So can you tell me what is the fix? Why it is not displaying anything? Can you tell me? Any guesses? Why it is not displaying anything? Ideally, it should print this failure message, but it is not printing. Why? Can anyone tell me? Very good. So we need the synchronization statement. So we need to add the CUDA device synchronize statement here. Right? So if you put the CUDA device synchronize statement here, then you'll be able to see the result failure message. The reason failure message is coming in because I'm not having a thread with this which is satisfying this condition because I'm launching only a single thread. Can you tell me the parameters to satisfy this condition? What parameters I should have? Please write in the comment what parameters I should be launching. What should be the configuration parameters so that the success message will be printed? Block says 256 and thread says 1024. Yeah, correct. Correct. So I need to have 256 blocks here. Instead of 1, I should put 256 here and I should put 1024 here. One more thing is, if I do like this, I will have failure messages so many times because most of the threads are not satisfying this condition. So in order to see the success message, let me comment this else part just to demonstrate only the success message is printed. So let me comment this else part. Why I'm commenting it? Because all the threads, all the remaining threads will make my output screen flooded with this message. So I don't want that. So I have modified the code, try to rerun the program. So if you see, it is printing success. Any question on this? Any questions so far? Any questions? Any questions? No questions, I hope. So let's go ahead. Now, so far, we have learned how to write the kernel, how to have the launching parameters, how to access the different threads uniquely. Not even, we are not know, but we know what are the different variables to uniquely identify the block, to identify the block dimension, to identify the bit dimension, right? And to identify a thread uniquely inside a single block. That also we know. So now let us go ahead and see how we can accelerate the problem. So if you look at this and is initialized with 2 to the power 20. So it's a huge number, and we are trying to take this number. We are trying to bring the numbers from 0 to 2 to the power 20 using a formula. Okay, so if I want to parallelize this particular for loop, I need two things to be done. Okay, so what is that? I need to launch a kernel. I need to write a kernel and print this and write this single line of code. So it will print that particular message, don't mean that. But again, I need the ID of that particular debate. So what is the ID? I can say what is the index that I'm going to print. So let us try to rewrite this particular code so that it is going to be executed in a CUDA kernel. So this is the code written at the CPU side. We will modify this code so that we will be writing it in the GPU side. So everyone again go back to the here notebook and click on the 01 single block loop.cu. So what we have to do here is once you open this file, you will see that it is having the code which will print the 0 to 9 numbers. So what we have to do is we want to refactor this function as a and make it a CUDA kernel which will launch to execute 10 iterations. So in this case, how many iterations? 10 iterations. 10 iterations in parallel. And after successfully refactoring, 0 to 9 numbers will be printed. Okay, so let me open this. Fine. So can you come back to LX again? We will discuss the code here, then we can go and modify the code in your notebook. Okay, so everyone is requested to come back to LX and see my screen. So here, this white loop is currently a CPU function. I want to make it a GPU function. So what is to be done? I need to put it global, right? So this keyword tells that this particular function is a device function, I can say is a kernel, and is to be launched from the CPU side and is to be executed at the GPU side. If you look at, there is a single parameter which is being passed, right? So this is the number of iterations that I'm going to have. Okay, so this is the GPU code. Therefore, I don't have to write this for loop here. So I will skip this for loop. I will simply have this print function here. Okay. So now see, I want to print the iteration number. Can you tell me how I can get the iteration number? Because I am going to execute this particular kernel in place, right? So I can get the iteration number in the name of thread number. Is it or not? Because ultimately the thread is going to execute this statement. So I can get the iteration number, or I can say I can get the kernel launch number by getting the thread number. Is it or not? So I will simply have. So can you tell me how to get the thread number in a block? Can you tell me what is the variable, CUDA variable to get the thread number in a block? Can you tell me? In a block variable. No, not index IDX. It is thread IDX.x. Okay. So I have to write this I is the instead of this, what I will write is thread IDX.x. Okay. So this will directly give me which thread is executing this particular function. Okay. Now this is done. Now let us change the function call now. Now this is a normal CPU function call. I want to make it a GPU kernel launch. So in order to make that, everyone knows that we have to put the triple angular bracket. Then now what is the question? The question is we want to launch enough number of threads. Okay, so they are saying you launch n iterations in parallel. N iterations in parallel means what? I want to launch n threads. Is it or not? So let us say I'm going to launch one block in and in each block. In that block, I want to launch n threads. So total how many threads are launched? Total n threads are launched, right? And this n can passing here. Okay. So as of now, I'm not accessing any. You can say I'm not initializing any data and all, but I'm just printing the things. I'm not manipulating any data as of now. So there is no menu management you have seen so far, right? So just after this modification, there is again one line is missing, that is CUDA device synchronize. So you just have this line. Okay, CUDA device synchronize. Now, if I save this code and execute here, you will see the code getting executed. Can you tell or you can get, can you see, have I used any loop here? No, right? A single statement is written. Again, this ID I have got with this variable, that is thread_id_x. Okay, so this thread_id_x is going to give me a unique thread number within a block. Here I am directly using thread_id_x because I know I am not launching many blocks. I am launching a single block. So obviously thread_id_x is going to give me a unique ID because I am having a single block. Okay, so within a single block, thread_id_x will ultimately give me the unique thread number. So I don't have to worry about it. Okay, any questions so far? Any questions so far? Any question? Expect the replies. Any question? Is it clear to everyone? Hello? Am I audible?
Yes, sir.
Okay, fine. So let us save this thing and after execution we will find this type of output. Okay. Now, if this is clear up to now, let us move ahead and just a small modification before moving ahead. Just for curiosity, you can have part y1 comma n. So let us try to launch n threads only, but n blocks and each block one thread. Is it also okay to launch the kernel with this particular configuration? Yes, it is okay because ultimately I am going to launch 10 threads, right? But the problem here is the output will be this is thread ID 0, this is thread ID 0. That message means thread ID 0 message will be printed 10 times. If you wish to see the output, you can see. So here I have got the iteration number 0, 1, 2, 3 output. The reason is I have launched 10 threads in a single block. Now I have changed equation such that I have 10 blocks with a single thread. So each block is having thread with the thread ID 0. So there the message will be this is iteration number 0, 10 times printed. So let us run the code. Have you seen the output? Are you on the Jupyter notebook or on the screen? Everyone please be on the screen, be on the WebEx screen. Just see the changes that I have made. I have launched this new kernel with m blocks having one thread each. And again, inside the kernel, I am accessing the thread ID x.x and printing the thread ID x.x. So this might, with this example, you might visualize that each block is having single thread with the thread ID 0. Therefore, if I run this code, I will get this message printed 10 times, but iteration number 0 will be printed because this message is printed by one block, this message is printed by another block. So each message is printed by different blocks. But thread ID 0 in each block. Are you ready? So let us say instead of n, I will put 10 only. So can you tell me what are the different ways to launch this kernel such that 10 threads will be launched? Can you reply in the chat? So I want to launch 10 threads. What are the different ways to launch 10 threads? Two ways we have seen. One is 1 comma 10, another is 10 comma 1. Is there any other way to launch 10 threads? Can you tell me? Can you reply in the chat? Very good. 2, 5. So let us launch this particular kernel with 2 comma 5. So if I launch this kernel with 2 comma 5, can you guess the output? The output will be, this is iteration number 0 to 5 will be printed by one block, 0 to 5 will be printed by another block. Let us see. See? 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So two different blocks are executed. And in each block, there are 5 threads. So this is, let us say, let us assume that this is block number 0, and this is block number, this is printed by block number 1. Let us assume. So I know you can visualize now. Now, if I change this 5 to, what will happen? 5 comma 2. This will again launch 10 threads. Then my output will be different. Why different? Because I have not written a correct code to correctly identify the particular thread. I am simply using thread IDs. So this is why there is a need to identify a thread uniquely inside a grid. So thread IDs is going to uniquely identify thread within a block, not within a grid. So that's what I'm trying to explain. So if I rerun this code, here is 0, 1, 0, 1, 0, 1. Because I have launched 5 blocks, and each block is having 2 threads. I hope it is clear to everyone. Any questions so far? Any questions? Any questions? Okay, fine. So I can see the correct responses from the participants. Very good. So this indicates you are getting the things. Now, I hope you have executed this in your notebook also. If not, you will have sufficient time later on after this workshop. You can practice. Okay. So just focus on the screen here on the robots. So there is another presentation which you can also access later on. So let us see. Now see, we know that on GPU we can launch the kernel, and kernel is executed, or you can say the kernel code is written such that a single thread is going to execute that particular code. So there is a thing in our mind that this particular code inside the function, or you can say inside the kernel, is going to be executed by each thread. So you write the kernel in a way that it is going to be executed by, you can say assuming that it is going to be executed by each thread. So I need to specify that, okay, this is the thread ID, this is to be done. If this is the thread ID, this is to be done, and so on. So I need the coordination between the different threads that are being launched. Is it or not? Because I am having many threads getting launched. But now the issue is how to identify uniquely. Just now you have seen, we are not able to identify the threads uniquely with just thread IDs.x. So we need some different mechanism for that. Okay. So let us say that the data is in a zero index vector. Okay. So if this is a vector, and the data is stored in this vector. So we are having 8 unit of data, and for this 8 unit of data, we have launched 8 threads to before. In a way that there are 2 blocks and 4 threads in each block. So total 8 threads are there. We assume that each, or you can say, we want to write a code in such a way that each thread is going to work on different work items, or you can say different data items. So how to make sure that each thread is working on its corresponding data? So for that we need thread IDs to be you can say the threads to be uniquely identified within a launch, right? So let us say this is my data which is indexed from 0 to 7. So 8 units, so 0 to 7. We are assuming that each thread must be mapped to work on each single element in that particular vector. So because we have one sufficient number, we can say exact number of threads as the data we are having. So if we are having 8 data items, we are launching 8 threads. So that each thread will work on each data item. So this is what we want to do. We know that each thread has, you can say, on each thread, if we call block.x, it is going to give us 4. The reason is block dimension is 4, right? Also, each thread within a block is going to have the same block ID as .x. So all the threads in this block are having 0 as block ID of .x. This block is having 1 as block ID of .x. This is clear to everyone? So this is block 0, this is block 1. Okay? And block 0 and block 1 both are having same number of threads. This is to be noted that each blocks in a grid are having same number of threads. So they are having equal number of threads. So this is both blocks are having 4 threads in them. Okay? Also, within a block, each thread has the unique thread ID within the block. So in this 0 block, the block thread IDs are 0 to 3. In this 1 block, thread IDs are 0 to 3. Right? And we can get this with the help of data.x. This is clear up to now. Now, you can clearly see thread ID.x 0 is for this thread, again 0 for this thread. So how to say that this thread is different from this thread? We can clearly see the difference in the block ID, right? So this is in the block ID 0, this is in the block ID 1. So in order to calculate the thread ID uniquely inside the grid, I need to take hint of block ID of .x also. So with the hint of block ID .x and thread ID .x, I get the thread ID, or you can say thread index uniquely within the grid launch. Okay, and this is the formula to get. Okay, so what is the thread IDX.x? Sorry, thread IDX.x plus block IDX.x into blockbook.x. This is very logical. The thing is, if I want to access, or you can say if I want to find what is the unique thread ID of this particular thread. So you can say, I want to first identify what is the block ID of current thread. So current block ID is 1. If current block ID is 1, I have to pass through all the threads in previous blocks. So how many threads are there in each block? There are 4, right? That I can get it with the help of blockdim.x. So blockdim.x is 4 into number of blocks up to this point. So how many blocks are there up to this block, there are one block, so that I can get it with the help of block IDs because my block IDs are starting from 0. So for this block, how many blocks I have to traverse? I have to traverse one block. So 1 into 4, total 4 threads I have passed. Plus, within a block, how many threads I have to access? I have to access thread IDX.xthreads. So what is the thread IDX.x? That is 1. So 4 plus 1, that is 5. So for this thread, the thread ID, or you can say the global thread index for this thread is 5. Is it clear to everyone? Any questions so far? Any questions? Or shall I repeat? Shall I repeat or shall I continue? Okay, fine. Let me. Okay. Let us say I am having. Sorry. Let us say I am having, okay, two blocks. Okay, so this is block 1, and here is the block 2. Let us say. Okay, so this is block with ID 0, and this is block with ID 1. Okay, now we know that each block is having same number of threads. This is clear to everyone. Each block is having same number of threads. So this block is having 4. This block is also having 4. Now let us say I want to find what is the global thread ID, or you can say what is the global thread number of this particular thread. So for finding the global thread number for this thread, let me give you another example. Just come to the real life world. Okay, let us say that I am having 2 rooms. Okay, in one room 4 students can be accommodated, in another room 4 more students can be accommodated, and you are having student enrollment number from 0 to 7. Okay, so I want to find where this student with the ID 5 is going to be accommodated. So just a simple mathematics, I will find how many students are there that can be accommodated in. Let us see another, you can say another way of explanation. But what is the ID of the student which is sitting in the second row, or you can say in the second bench, in the second row? So what is the global? I want to find the ID of this student. I know that there are only 2 rooms. Each room can accommodate 4 students. And I know what is the room number that I am in. That I can get it using the block IDX.x. So block IDX.x you can think of it as a room. Okay. So this is block IDX.x. So this is room number 0. This is room number 1. Okay, so I know I can get the room number from here. So I am in the room number 1. That I can get it with the help of block IDX.x. So I know what is the room number. So if it is 1, I know already there are 4 students already accommodated in the previous room because I am in the second room, right? So in the first room, 4 students. So 0 to 4 IDs are exhausted there in the first room, right? So that I have to find out. So how I can get it? I can get the room number, or I can say block number with the help of block IDX.x. So because our IDs are starting from 0, I can directly multiply that ID with the number of students per room. So what is the room ID? Room ID is 1 into number of students per room. Number of students per room is 4. So 1 into 4 is going to be 4. So this is the total number of students already accommodated in the previous rooms that I am having. Okay, so total 4 are gone. Or you can say 4 IDs are exhausted. I want to find the current student ID. So obviously 4 plus within a row, what is the unit ID? So within a row it is second, right? So that I can get it with the help of head ID and x. So 4 plus 1, right? So this is 0, this is 1. So thread ideas dot x also starts from 0. So 0, 1, 2, 3. 0, 1, 2, 3. So block dim dot x into block idx dot x is going to give me the number of threads accommodated in the previous blocks plus number of threads in the current blocks. So how many threads? Its ID is 1, so plus 1. So total 4 plus 1, the ID will be 5. So if you look at the global, so this is 0, 1, 2, 3, 4, and 5, 6, 7. I hope it is clear now. Is it clear? Okay, fine. So this will give me the unique thread ID, or you can say unique thread number within the thread. This formula. So we are getting block ID dot x into block bin dot x. So what is the block ID and how many threads per block are there? So this will give me the previous threads accommodated in all blocks up to now. Now I will come up to here. Okay, up to here. Now, if I want to find the thread number, thread ID, unique thread ID of this particular thread, I first find what is the thread, what is the block ID. So I want to come up to this point. So up to this point, how many threads are there? That I can get it with this formula, block ID dot x into block bin dot x. So this will give me a total number of threads that are already accommodated in the blocks plus thread ID dot x. So now I have come up to here. Now, what is the offset I have to move ahead? So that I am going up with the help of thread ID dot x. So this will give me the unique thread number within the thread. Okay, so this will give me the visualization. This will give me the visualization. So thread ID dot x is 0. Block ID dot x is also 0. And block dim dot x is 4. Right? So this block dim dot x is going to be the same for each thread because all blocks are having same number of threads. Is it or not? So this 4 is going to be constant. What is going to be changed is these two things. Also, this thread idx dot x is going to be different. Sorry, this block idx dot x is going to be same for 0th block and 1 for first block. Okay, so for this thread, what is the global thread ID? So the formula is 0 plus 0 into 4. So it is 0. Again, right? So our question was, what is the data ID that this thread is going to access? So that I can clearly see that this thread or this thread, what is the thread ID dot x? Can you tell me? What is the thread ID dot x for this thread? It is 1, right? It is 1. What is the block ID dot x? It is again 1. What is the block bin dot x? It is 4. So if you put the formula and calculate, you will get 5 of the answer. So this thread will work on this particular data. and so on. Any questions so far? Any questions? Is it clear to everyone? Any questions? I hope it is clear. Not clear yet? Okay, fine. Now, with this, I can find the unique thread number using grid. So next, what we want to do is we want to create multiple blocks and within the block multiple threads. So that program we are going to do. So everyone, first look at this particular my screen now. Then you can work on your code. Okay. So I will click here. So what they have asked, let us say. So currently this group functions and runs for loop in serially print this 0 to 9. If we have, so I have not made any changes. So first see what is the output. So it is going to print this in a sequential way because we have not changed anything. This is the CPU code. Okay. What we are asking is you have to refactor this code such that 0 to 9 should be printed in a CUDA kernel. Okay. And for this execution, use the configuration which launches at least 2 blocks of threads. So can you tell me what is the launching parameter I should be using now? What is the launching? Please don't look at the solution. What is the launching parameter I should be using? If I want to launch 2 blocks, how many threads per block I should be using? 2.5. Good. So I should be using 2.5. Right? So here launching parameter should be 2.5. There I have to make the change. I have to make it underscore global underscore. And then I have to remove this formula because its name is going to work on it. Earlier, we were using thread ID.x directly, but it was not working, right? So with the knowledge that we have got from the previous presentation, can you tell me what should be the value of I? So we will first calculate the value of I. Int I is equal to. Can you tell me what should be the value of I? From the previous slides, we know that this I is going to be the unique thread number within a thread, and we know how to calculate. So the calculation is thread ID x dot x plus block ID x dot x into block name dot x. So this will give me the unique thread number within a block. Okay. So in this case, what I am doing is I am launching 2 blocks of thread and each block is having 5 threads per block. Okay. So with this formula, I will get a unique thread number getting printed as the iteration number. Okay. Previously, we are not using this formula, we were directly printing thread ID dot x. So the problem was 01010 was so 02 4 02 was printed. But I want to print 0 to 9. So that we can get with the help of this formula. So let us save this code and rerun the code. Again, there is a problem. Why? Can you tell me? What is the problem here? Why my code is not working? Anything that is not variable. So I need to add the CUDA device synchronize statement. Okay. I need to build the CUDA device synchronize function here. Now if I do that, you can see the code is displaying this type of output. You might have noticed that the iteration numbers are printed out of order. 0 9, it is not in order. Like 0 to 9, it is not displaying. It is displaying differently. The reason is the blocks are scheduled by the scheduler randomly, and we don't have control over it. So we don't know which thread is going to execute when, which block is going to execute when. So can you guess this thread number, this iteration number is printed by which block? Block 0 or block 1? Can you reply? This iteration number is printed by which block? 5. I know that how many threads per block? 5 threads per block. And there are 2 blocks. Okay. So the thread ID 5 is printed by which block? Block 1. So how I can get that? Can you tell me how I can get that? If you wish to get the block ID also, that okay, this is the block ID in which I am working in. You can also create that. You simply have to write block ID with that. Get that. Okay. So you can do many experiments with this code later on. Okay. So we will move on here. Okay, one more thing that I want to tell you is that even if this 2 file is there, let us assume that I'm having 1, 10. So if I launch the kernel in such a way that I'm launching a single block of threads and up to 32 threads, so in the block. So if there is a single block of thread, the threads will be working in a lock state. Lock state means that they will be synchronized amongst themselves. So here, even though you might be thinking that 0 to 10 into 0 to 9 into displayed out of order, but that is not the case. The reason is they are locked in a single block. So within a block, the threads will execute in synchronized manner. So if you again we check, we will see all the threads are working such that thread 0 will execute first, then 1, 2, 9. The reason is up to 32 threads. So I am saying work of thread executes in a nutshell within a block. Okay, so it is an advanced concept, no need to worry, but still for your knowledge I am telling. Again, if I say 10, 1, the thing is you will get the output out of order because we are launching 10 blocks with a single thread per block. So I get the out of order output. And this order will change in every execution. Okay. Now, everything is done up to now. We are able to launch the different threads, different blocks, and we are able to access the unit threads uniquely within a thread. Now, it's time to work on the data, and for working on the data, we should have the data in a GPU, right? And as we have seen in the presentation earlier, that is being done with the help of CUDA analog managed. So CUDA analog managed is the function which is used for allocating the memory to the variable both to the CPU as well as the GPU. Okay, so this you might have been using earlier in a C. So this is the CPU only code to allocate the memory for a variable. So this analog function allocates the memory to the variable at the CPU side. But because we are writing in this program, we are trying to execute the code at the GPU, so we need the mechanism to allocate the memory both at host as well as the device side. And that is done with the help of CUDA analog managed. So this function, what it does is it allocates the size amount of memory and returns back a pointer to that particular memory in A. Okay, so what is A? A is a pointer, integer pointer, which points to some memory location. That memory location is accessible both by CPU as well as GPU. The reason is we are allocating that memory location with the help of CUDA analog managed. So, in a summary, if I am going to use CUDA analog managed function, that particular memory is going to be accessed both by host as well as device. So this concept is known as unified memory concept. So unified memory means what? The particular portion of the memory is accessible to both CPU as well as GPU. So I don't have to manually transfer data from CPU to GPU or GPU to CPU. It is taken care by the runtime. Okay, by the CUDA runtime. So this is taken care by this particular function. So internally, the data transfer will happen. So I don't have to worry about it. I don't have to manually transfer the data from here to there. We just have to create the variables in this way so that the variable is accessible to the CPU as well as to the GPU. Is it clear to everyone up to now? Any question? Any questions? Please let me know. Is it clear? Are you all waiting? Okay. Anyone reply? Okay, fine. If any question, please interrupt, okay? I'm there to help. One more thing is that this is, let us say, this much amount of data I want to work on. Okay, so this is the size, or you can say this is the amount that I want to work on. Now, these many data items I want to store such that they are accessible to the CPU as well as to the GPU. So for this, first I need to know what is the type of that particular data. So the type of the data into amount of data will be the total size in terms of bytes to be allocated table. Okay, so this is the calculation. So you can say size is equal to n is the total number of elements that I want to store, and size of elements, size of each element. So let us assume that all the elements are integers. So I want to store n integers in a memory. So how much memory I will need? So obviously I will need n into size required to store in single element. So let us say where I am having 100 elements and size required to store each element is 4. So how much amount of memory I will need? So 100 into 4, that is 400 units of memory I will need. So that's what is stored in a size. So this is how you can calculate. Then next is that memory is to be pointed out by a variable which is accessible to both CPU as well as GPU. So and then I don't know the variable which points to the memory location is a pointer. So you will define a pointer which will point to the int private. So that's why the type of this pointer is int. So int star a. So this pointer is created. Now we call this CUDA alloc managed function such that it will allocate the memory of size units and give me the pointer, or you can say make a to point to that particular memory. So it is very it should be noted that I have to pass the address of that pointer here as a first parameter, and the second parameter should be the size in the unit in the bytes. Okay, so that how much bytes I want, and he should be pointing to that particular value. So here, after this allocation, I will be able to use a both on CPU as well as GPU in the heterogeneous accelerated system. Now, it is the best practice to deallocate the resources, or you can say deallocate or free the variables that are not being because garbage collection is not there in C, right? So we need to free the memory that is used already. So which is of those. So that is being done with the help of CUDA free function. So CUDA free, and what memory you need to use, that you pass that. Okay. So I hope it is clear. Fine. So let us try to see this particular exercise. So we will be working on this exercise. So this program will allocate an array initializers with the integer values on the post. So initialization function is a simple function, and it attempts to double each of these values in parallel on the GPU. So the doubling function should be a global function, or you can say a kernel. Okay, and then it confirms whether both doubling operations were successful on the host. So this verification function is written at the CPU side. Okay, currently the function won't work because maybe the launching parameters are incorrect. So let's see the code. So as they have mentioned, the initialization function should be done at the CPU side. So this is okay. We don't change this code. Now this double elements in parallel GPU is to be written as the GPU kernel. So our first condition, then it should start with the underscore global. These are conditions, so it is correct. Why? So this is correct. So what is wrong is, let us see. So in I, here I is the unique thread ID within the thread. Okay, so it is finding the unique thread ID. So block ID is dot x into block dot x plus thread ID is dot x. This is also correct. Now this global ID we are checking whether it exceeds the total number of elements. So it does not exceed, then only you double that in. So this is also correct. So this code is correct. Let us see the launching parameters now. Are you all with me? CUDA alloc and CUDA alloc managed. Okay. So now actually CUDA alloc will manually allocate the memory, and in that case the data movement should be done manually by our end, by the programmer. Okay, and it does not work with the unified memory. And if you allocate the memory in the envelope managed, you are using the unified memory concept, thereby reducing the programmer's load to you can see manually transfer the data. So in this case, we have to use the different calls to like pull and copy functions to transfer the data from CPU to GPU and from GPU to CPU. So that is the additional things that you have to take care of if you are using the CUDA analog. But if you are using CUDA analog managed, you don't have to worry about the data transfer because both CPU and GPU are pointing to the same location. So you are not ideally going to transfer the data. You are just accessing the memory directly. I mean, it is clear to you. And hello? Okay, fine. So we were here. If you look at the line number 57 in the code, they have not allocated the variable A in the unified memory. So we need to somehow change this statement so that it will be allocating this A so that it will be accessible at CPU as well as GPU side. So can you tell me what changes I should make here in this line 57? Can you tell me? Anyone? Very good. So I have to use the CUDA analog. So let us change this line. So what I do is I will comment this particular thing and I will divide my code over here. I know size is already deployed. Yes, it is deployed and it is calculated correctly. So this function is going to allocate the memory such that that particular portion of the memory is accessible by host as well as device. And it is made possible with the help of CUDA analog managed. So here I am using the concept of unified memory. Okay. Now, is it A comma N? So can you tell me what is it a kernel launch or it is a normal CPU function call? It is obviously normal CPU function call. So init function is written here, right? So the call will go here. So the array will be initialized with the ID of that particular element. So 0 to 10 will be initialized. Okay. Then next is we are having launching configuration variables being initialized here. So in this case, can you guess how many threads, total threads are being launched here? Divided thread number of blocks is 10 and number of threads per block is 10. So how many total threads are launched here? Can you tell me? How many threads per block are launched here with this configuration? 10 into 10 is 100, correct. So total 100 threads are launched. But if you look at what is the size here, it is hard-coded, okay, and it is also 100, and we are launching 100 threads. So I don't know it will work fine, but normally this is not the case in real applications. You have to test it. So because it's a first code, we have hard-coded, so we will go with this one. Okay, so we won't change this. So if number of threads per block is 10, number of blocks is 10. Now, this launch will not work until pointer A is also available to the device. And this provision we have made in this particular 59 number. Right? So now it will work. Is it a kernel launch? Just see. Yes, it is a kernel launch. And what is the configuration? It is number of blocks, that is 10, 10. Okay. A and N are the inputs to my kernel. What is A? A is the memory location on which I am going to work. So what I am going to do? I am simply doubling the indexes or doubling the elements. So earlier, if the value of A of 1 is 1, now it will be A of 1 is 2. A of 2 will be 4, A of 3 will be 6 and so on. Okay, so this will be done. Now, this will be done in parallel in 10 blocks, and each block 10 threads. So 100 threads will be working parallelly on this particular memory, and they will be typically doubling the particular index based on the index of that particular thread, global index of that thread. Okay, and that's what we have to make sure that the thread is accessing the unique data. There is no data should be accessed by more than one thread. Otherwise, the results will be wrong. So this line is making sure that each thread is accessing a unique, or you can say its own data, not the other's data. Okay, so here I am getting the thread ID, global thread ID, and I will be updating that global, or you can say that unique data only. So each thread, each of these 100 threads will be launched simultaneously. They will be updating the elements simultaneously, and they will come back. The result will come back. I don't have to transfer the data back because this A is also accessible to CPU. Is it or not? So CPU is also able to see the changes that the CPU has made. The reason is A is allocated with the help of CUDA and alloc manage. So I don't have to worry about the data transfer. Okay, now this CUDA device synchronize makes sure that CPU won't access that particular memory which is being modified by the GPU kernel. So that's where the synchronization comes. So we normally synchronize when the same memory is going to be accessed by more than one, is we can say complete units, right? So here we are making sure that CPU is waiting for GPU to complete its task. Now once the task is completed, CUDA device synchronize will make sure that the task is completed at the GPU side. Then the CPU version of this verification function will be executed, and it will return either true or false. So if elements are all elements are double, it will return true, otherwise it will return false. Right? So this is what the code is. Again, here we have to, because we have allocated the memory to the A with the help of CUDA and alloc managed, we have to release the memory with the help of CUDA free. So just change this to CUDA free. Okay, so now this is done. Let us try to execute the code. The output should be true. Yes, the output is true. Is it clear to everyone? This code is clear to everyone? Any questions? Any questions so far? This CUDA envelope managed first line manually allocating manually GPU and copying from CPU. No, not actually. It is for our convenience. The idea out there. It is for our convenience. It is for programmers' convenience. That we are internally, that also we will see in the lab that even though at the high level we are not seeing data transfer, but at the low level there is a page fault happening because the data is loaded and unloaded at the back end to the domains and to the host. So yes, the memory transfers are happening, but the thing is, it is taken care by the CUDA real-time system. So yeah, CUDA and the lab is little bit faster. So manually doing this is fast, not much, but because of the convenience, most of the people are using unified memory because we don't have to worry. Also, the size or you can say the amount of memory available only to the GPU is less. So better to use the unified memory, which is bigger, right? You can say that the particular data we don't have to. One more thing is that if you use the CUDA and alloc, you have to actually copy the data Hello? Am I audible? Hello? Hello? Am I audible? Sorry, there was issue at my end. I got logged off. Uh, Sorry for this. Aditya, was my explanation clear to you, or you are not audible? I was not audible to you. Aditya, can you come please? I did not know when I got logged off during explanation. I was just explaining. Okay, fine, fine. Thank you. Thank you so much. So, yeah, this this will do us. Let's go. So let us now try to change the configuration such that we meet the requirements. So let us say block id is not x. Okay, I think we were up to memory allocation. Right. Right. So any questions so far? Any questions? No questions, right? So let's go ahead with the grid size work amount mismatch. So after whatever the bunches were done, the bunches were matching with the total amount of work that we had. Like earlier we wanted to work on 100 word items, so we launched the 100 threads. But it is not always that we are having sufficient amount of threads being launched or launched. So in that case, we need to um, think of the configuration mismatches also. Okay, so let us see. Let us go through the different conditions first. So let us say n is unknown to us. Like I mentioned earlier that n is hard coded. So let us say n is known to us. That is, let us say this much, and we have the threads per block. So this is 256. So now if I want to launch 256 blocks of threads and such that I want each item to be covered with the number of threads. So I want to launch sufficient number of threads such that all the data items will be covered. Hello? Oh, sorry. Sorry. Is it possible now? Now? Oh, so sorry. Right. So I was meaning we have seen how to allocate the memory, unified memory to the data items that we want to work on. And up to now, we have seen the condition that we are launching the same number of threads as there are data items with us. There might be the case that we are launching more than the required amount of threads in our kernel launch. So what to do for that, for those threads? So let us say I want 100 threads, but I am going to launch 1000 threads. So what will happen to the remaining 500 threads? They should be sitting here, right? Only 100 threads should be working on the data. The remaining 900 threads should be kept able, so they should not do anything. So I should have a mechanism to handle such mismatches. So that's what we will see now. So let's go to this presentation. I hope all are following me on the WebEx. So up to now we were like we have same amount of data and same amount of threads got launched. Okay, and the amount of thread, or you can say number of threads are exactly the same as the amount of data. But what if we are not having enough, or you can say more number of threads compared to the data to work on? So let us say I am having only 5 minutes of work to be done, but I have launched the kernel in a way that I am I'm working with the 8 threads. So I have to write a code in such a way that I should mention that these 3 threads out of 8 threads should not do anything. So what needs to be done? So I should write the if condition, and in that if condition I have to check whether the total number of threads, or you can say the given thread ID exceeds the total number of data that I am having. If it is exceeding, don't do anything. But if it is not exceeding, do following things. So that that I have to put in the if block. Okay. So I will check if a given thread ID can work or not work. So based on the condition, I will decide whether to continue or whether to just set it out. Okay, so for this particular thread, the ID comes out to be 4, and which is true because 4 is less than 5, right? So 4 is less than 5, so this will work. But for this thread, the ID becomes 5, right? And data index becomes 5, which is less than 5, which is not less than 5, which is equal to 5. So this condition will be false. Is it or not? So therefore it won't work. Same for the remaining 3 items. So this mechanism we have to implement in our code. So let us again revisit this particular code wherein we have n which is given to us, and we want to decide the number of threads based on the number of blocks we are launching. Normally, number of threads per block, we take it as a multiple of 32. I will tell you the reason later, but as of now, just remember that the number of threads per block should be multiple of 32. So this is the thing that you need to take care of. Okay, so number of threads per block is multiple of 32, that is 256. Here, data size 1. So if I am having 256 threads and total this many data items I want to work on, so how many blocks I need? Can we do the mathematics here? If I am having these many data items and I am having 256 threads per block, so how many blocks I should have? So if you calculate it, you will get this divided by 256. So it is coming out as a fraction. Can you see? 390.625. So how many blocks I should launch given the number of threads per block and amount of data that I am going to have? I should be in a position to identify the number of blocks to be launched. Okay, so in this case, the amount is coming in a fraction. So what I should take? I should take this zero, not the floor, right? So I should be launching 391 blocks of 256 threads per block. Am I clear? Up to here? Am I clear? Any questions? Any questions so far? See, we are now at the launching parameters. Launching parameter contains 2 things: number of blocks and threads per block. Up to now, we were launching the kernel with the same amount of threads as the data items. So what we were doing, it is 100, we were adjusting this configuration parameters. But now let us assume that I want to launch the threads per block which is multiple of 32. Let us say 256. So I want to launch 256 threads per block. So how many blocks I will need such that I will have the sufficient number of threads to cover these many items. Obviously, for that I need to divide 256 to this number, and which is a fraction. So if fraction is coming, I have to consider the upper bound, not the lower bound. Because if I consider the lower bound, I will end up in launching this number of threads. So it is okay to have more number of threads than required, but not okay to have less number of threads. So here in this case, I will launching more number of threads. Okay, so how to calculate that number is put the look at this formula. N plus threads plus blocks minus 1 divided by threads per block. So this will give me the exact number of blocks that should be launched. Okay, is it clear to everyone, or should I explain with clarity again? This formula is clear to everyone? Let us take, please let me know. Am I audible? Hello? Am I audible? Okay, so this formula will give you the total number of blocks given the threads per block and the n size. Okay, so in our problem statement, you will be given the total amount of work to be done. You will be launching the threads per block, which is multiple of 32. Ideally, let us say 256. Okay, so if I want to launch 256 threads per block and I know the total size of the data, I must calculate how many blocks I should launch. And for that, this is a simple mathematics that I should follow. Okay, so these many blocks I need to launch. So this with this I will get number of blocks and threads per block. So these two parameters I will pass and then they will be kernel mount. Now it is obvious that I am having more number of threads than required. So the if condition is necessary in this case to check to make sure that the particular thread ID, or you can say the particular thread index should map to some value within that. If it exceeds n, you don't do it. If it is within n, you do something. Are you getting my point? So let us assume I am having 100 elements. Okay, and I want to launch 32 threads per block. With the simple mathematics, can you tell how many blocks should be launched? How many blocks should be launched? Can you tell? Such that there are sufficient number of threads to cover these 100 elements. With one block, I will cover only 32 threads. With 2 blocks, I will be able to cover only 64 threads. With 3 blocks, I will be able to cover 100 elements plus 8 additional elements. So I will need to come up with the value 3 as the number of blocks. So let us see how it comes. Okay, with the formula that we have. So what is the total number of elements? Total number of elements is 100 plus. What is the threads per block? Threads per block is 32 minus 1. Okay, divided by 32. So what will be the value of this? Let's find. It should come up as Sorry, not three. We should have four blocks because with three only 96. Up to 96 only we will be counting. So up to four, we take four blocks, right? Is it clear to everyone? Any question? Is it clear? Okay, fine, fine. Sorry, that was my mistake. So we made four blocks, and that we can come up with this formula. Okay, so this formula will give me the exact number of blocks to be launched when we have threads per block. Okay, so obviously with the four blocks launched and there are 32 threads per block. So 4 into 32 will be the total number of threads we want. So total 128 threads are launched. So up to 100 threads we are fine. But what about the remaining 28 threads? So that condition need to be given so that we won't have many invalid data accesses. So for that we need to check whether the given thread ID exceeds in total n. So in this case, let us say 100. So that ID should not exceed 100. If it is exceeding 100, you don't do anything. But if it is within the limit, you do this particular task. So this is how you handle the data mismatches. So let us take the second exercise. So mismatch output loop.cu. Let's work on this. So after this, we will have a lunch break. Okay, so just pay attention. So in this program, it is allocating the memory with the number of program we have managed for 1000 elements. Okay, then it seeks to initialize all the values of the array in parallel within the CUDA kernel. So the initialization is happening in CUDA. In kernel. Okay, so this program assumes that both n and the number of threads per block are given. So number of threads per block is given to us, and n is also given. Our task is to complete these objectives. So what objective? The first objective is assign the value to the number of blocks that will make sure that at least as many threads as there are elements in one block. So let's see. So this function is correct. We will have to pay attention here. Our main aim is to. So again, here the memory is allocated correctly. Modified memory is allocated correctly. Now again, assume that we have reason that different threads per blocks are not, so we don't have to change this. Okay. Now here I have to modify the number of blocks in such a way that I will be able to cover all the n elements that are there. So can you tell me the formula for this? Can you write the formula in the chat? So the formula is thread ID is what? N plus how many threads per block are there? So that is already defined here. Threads per block. Okay. Minus 1 divided by threads per block. So this will make sure that I am launching enough number of blocks to accommodate 256 threads per block such that I am having enough number of threads to cover 1000 elements. Okay, so this is the formula I have to put. Now initial value is 6. So I want to initialize all the elements with the value 6. Okay, so initial value 6 I am passing, the array I am passing, and the n is the size, that is 1000 I am passing. So here is the call, here is the call to the CUDA kernel. Okay, So that's what we want to change. So that's it. So this is the change that we have done. So let us save this code. Okay. Just wait. Okay, we'll do everything. I think that this is some issues again. We have a lunch break. Am I audible? Hello? Hello? Am I audible? Hello?
Is my screen visible? I hope the screen is visible. Okay, fine. Thank you. So before lunch, we were discussing the uh, launching parameters in a way that there is a mismatch to the number of data items and number of threads being launched. And we discussed that there should be a check to identify the thread which should not work for a given computation. Okay, so and there is a we should apply the if condition to check for the ID of that particular thread which is working, and if it is exceeding the total number of elements, we should not do anything for that particular thread. Okay, so let's try to modify the code in a way that we launch the enough number of more than enough number of threads, and we handle the situation in which the threads launched are more than the actual required threads. Okay, so we were discussing this program. In this we have this kernel which is initialized. Hello, am I audible? Priyanka ma'am, you are unmute, I suppose. Please mute yourself. Priyanka ma'am, please. Okay. So this code, we are trying to initialize the elements of A array with the particular value, that is initial value, and n elements that in that array. The value of n here is 1000. Okay, and we are knowing the number of blocks, sorry, number of threads per block. We are knowing the total size, the total data size also we are knowing. Now we want to calculate the number of blocks that should be launched, discussed right before lunch. So the formula for this is, if you can remember, is thread id, sorry, threads per block plus n minus 1 divided by threads per block. Okay, so this will launch the enough number of threads uh, to handle the uh, given data elements. In fact, more than enough. Okay, so we have to check if the threads are accessing the valid data or not. Now, what is meant by valid data? Let us assume that we have allocated the size, the memory of the 1000 elements, and our thread ID 1001 is trying to access the location 1001, which is not existing, right? Because the GPU won't be able to access that because we have not allocated it. So that case we have to handle, because in this way our GPU is to access the invalid memory. So for that we need to put the if condition here. So here you calculate the ID of that thread with this formula, right? Now here you put the if condition. Inside if condition, you check if the calculated index of thread is less than the total number of elements that is required. Okay, so what is the total number of elements? We have already passed it as a n. So the value is 1000, right? So every time each thread will calculate its own index. Once it is calculated, it will check if its index falls in a range of 1000. So if its index is less than 1000, it is ready to work, or you can say it is allowed to work, or you allowed to initialize that particular memory location. But if the ID of the thread is exceeding 1000, that means what? We should not allow that thread to access the invalid memory location. So therefore, in this particular way, we are handling the launch parameters, which are you can say which are allocating more number of threads than required. I hope you understand, right? So here that modification we have done. Now the next thing that is to be done is, yeah, I think now it should work. Now the code should work. So we have modified the code with two things. First thing that we have changed is the number of blocks we have changed. The second thing is we have introduced the if condition. Okay, so now let's try to execute this. So if you say you will get a success message. Are you able to follow me? Are you getting what we have done, or any explanation is needed? Hello, am I audible? Please reply, because I am facing some technical issues. I don't know whether I'm online. Okay, okay, fine, fine. Thank you. Fine. So uh, let us say that we remove this if condition and see what happens. Okay. So if I remove this if condition, what will happen is my launched threads will have some of the threads will be accessing the invalid memory location, and uh, which will not which we don't want. Okay, so let us try to execute this code again. So in order to check whether our kernel is successful or not, there is another concept, that is CUDA error handling, that we will be seeing in the next chapter. But just for the sake of understanding here, we will try to catch the error that has happened while launch of the kernel. So here what we will do is we will initialize one variable, that is CUDA error underscore t is equal to CUDA get last error. So what we are trying to do is we are trying to print what happened inside the kernel, because see, if there is anything happened in the launch of during the kernel, so it will not show any error to us. But if we want to catch what happened inside the CUDA kernel, so we can do that with the help of CUDA error underscore t variable, that is error. So this variable will store the errors that are going to occur inside the CUDA kernel. Okay, so that first we will initialize it with the CUDA success. Okay, so we assume that our kernel launch is successful. Okay, so I will do this before the kernel launch. Okay, so this is error handling we are looking at. Okay, so we have initialized our variable with the CUDA success. So CUDA success is again the uh, CUDA keyword which indicates that the kernel launch or kernel execution is successful, and we are assuming that it is successful. Now after the kernel launch, after the CUDA device synchronized, this CUDA device synchronize will return us the error code, whether it is success, CUDA success or failure after the execution. So this CUDA device synchronize will tell us whether there is problem inside the kernel execution. We know very well that the kernel launch is successful. Kernel launch, there is no problem in the kernel launch. So we are not checking for the error in the kernel launch. We are checking for the error in the you can say GPU code, right? Inside the kernel, is there any problem? So that we can check with the help of the error code that we got from the CUDA device synchronize function call. So if we print this particular, so it will print the with the help of %s, or you can say, so this CUDA get error string is a function which to which we pass this variable, which will display the error message that is being occurred, or you can say error message that is being passed by the CUDA runtime system. So here we are checking if error is not equal to CUDA success. So this will be executed only if the kernel execution was not successful, and we know it is not successful because we have launched the we have launched the threads which are more than the required, and we are not checking for the boundary conditions here. Okay, so let's rerun the code. If you look at the just wait. Okay, we will visit it when we are actually at the error handling. So just moving ahead. It was just for demonstration purpose. We will come back to this particular code when we actually are equipped with the error handling. So just make a note that you have to deal with the boundary conditions when you are launching more number of threads as required. Okay, so that was the point I wanted to make. Okay, so uh, now this is one case. Another case is, am I audible? Am I audible? Hello? Am I audible? Okay, fine. Thank you. Now, uh, in the previous case, we have launched more number of threads than required. Now, there might be the case that we are launching less number of threads than required. So what to do in that case? So in that case, one thread will have to work on more than one data element at a time. Is it or not? So that also we have to handle, and that is being handled with the help of grid stride loops. And this is the very common strategy which is being followed in real life applications uh, because there are cases wherein you have huge amount of data than the total number of threads that you can launch in a kernel. So there is limitation for launching of threads in a kernel. So if that limitation reaches and still if you have huge amount of data left, so in that case we go ahead with the grid stride loops, wherein in we have iteration inside the kernel wherein one thread will work on many data items. Okay, and we distribute the data items to each thread. So that strategy we will follow. So let us follow this presentation, then you will have clear idea. Okay, up to now we have seen the data elements and equal number of threads are launched for the processing those data elements. That was the case one. Case two that we have seen is we have particular number of data elements and we have launched more threads than required. Right now, this is the third case wherein we are having more data elements but less threads are launched. Like in this case, there are 8 threads launched, but we have total 32 data items to be processed. So logically, each thread should work on 4 data items. So let us say this thread 0 should be working on not only on one data item, but it should work on 4 different data items. Like 0 should work on this data item, then this, and this. Okay, so normally the examples that we have seen so far was like this, that each thread was working on a single data element, right? But what about the remaining 24 data elements? Only the 8 elements are processed by the 8 threads, but we have 32 data elements. So what to do in this case? So the answer to this is we have to distribute the remaining data elements again to these 8 threads. Okay, so the red portion of the data items are left for allocation. Now there should be a strategy which is to be followed so that each thread will get equal or at least similar amount of data to be processed, right? So one way is, the answer to this is we should use the grid stride loops. Now, what is the grid stride loops? Grid stride loops is nothing but the uh, we initialize the stride with the size of grid. Can you tell me what is the size of grid here? What is the grid dimension here? Can you tell me? What is the size of grid? I'm not asking you about the grid dim.x value. I'm asking you about the size of grid. Size of grid is nothing but total number of threads that are launched in a given grid. So how many threads are launched here? Total 8 threads, right? So the grid stride loop will allocate the value of 8 to the stride variable, and we apply the for loop wherein we increment the value by 8. So every 8th element will be processed by the given thread. So for example, if thread id with the 0 will process first 0th element, then 8th element, then 16th element, right? So every 8th element it will process. Are you getting my point? Any questions? Any questions? Any questions so far? Am I audible? Am I audible? Hello? So this is the concept of grid stride loop. So in a grid stride loop, the thread's first element is calculated as usual. Like the first element is calculated with this formula that we know already. But the next element to be processed by this thread is calculated, or you can say the next element is known by adding a stride value. And in this case, what is the stride value? Stride value is the grid dimension. Is it or not? So the grid dimension is 8. So 0 plus 8 is 8. 8 plus 8 is 16. 16 plus 8 is 24. So these are the data indexes that is to be processed by thread with the index 0. Okay, so if you follow this visualization, you will clearly understand that this value, that is uh, thread ID, is added in each iteration with the stride value, that which is 8. So the 0th thread will access 0th element, 8th element and 24th element. So if you continue this way until data index is greater than the number of data elements. So if you look at, we are at the 24th position. Now if you again add 8 to this 24, you will get 32, which is not greater than, or sorry, which is not less than 32, right? 32 is equal to 32. So the condition will fail and we won't work for that particular iteration. I hope you are getting the point, right? So with all threads working in this way, the elements are covered. So even though we are having less amount of threads getting launched and huge amount of data to be processed, you can actually work on this data with the help of grid stride loop strategy. So now the question is how to calculate the stride value. Can you write in the chat how you will get the stride value? Any guesses? Can you think of how to come up with the grid value? I'll wait for 2 seconds. Please reply quickly. My question is how to find the value of stride. Can you give me the formula to calculate the value of stride? I'll give you the hint. The stride value should be equal to the total number of threads that are launched. One more thing, these launching parameters multiplication is equal to the total number of threads, or you can say the grid dimension. Okay, but these 2 and 4, these are not available at the GPU end. You don't know these values. So somehow you should know what is the representation of these two in CUDA variable form. So what is this variable? Also, what is this variable? So if you multiply these two things, you will get the grid dimension. I hope you can guess. So number of blocks into threads. I want the CUDA statement for this. So this is number of blocks into threads per block, right? So what is the variable to identify the number of blocks? Grid dim into not block ID. Block ID will give you the ID of that blocks. Okay. I want the number of blocks being launched. So that we will get with the grid dim. So this grid dim, so Anjali has correctly answered. So grid dim is the number of blocks being launched and block dim is number of threads per block. Grid dim means number of blocks per grid and block dim means number of threads per block. Okay, so this multiplication will give me the stride value. Okay, so this is how you come up with the stride value. And with this logic, if you go ahead, each thread will have So this is for the first iteration. For the second iteration, the threads will be accessing these elements, respective elements, right? In the third iteration, again, it will access this. In the next iteration, it will access this. So this is how you get the um, working of your kernel, and you allocate the given number of data items to the threads. Okay. So this was the example wherein our data set is much more larger than the total number of threads that we have launched. Okay, so let us assume that we have, so we will perform all these things. Okay, so grid stride, with the help of grid stride. So we will work on this example now. 03 grid stride double dot cu. Okay, so in this, what we have to do is, we have these many elements. Okay, now this is fixed now. Okay, we are not going to change this configuration, right? There are 256 threads per blocks, and total 32 blocks are there. So in total, how many threads are launched? If you do the multiplication, so 32 into 256, total 8192 threads are launched, but number of elements that are to be processed is 10,000. So what about the remaining elements? Who will take care of those elements? So therefore, there is a need of stride loops here, is it or not? So the grid size is 8192, but the total number of elements are 10,000. Now we have to make sure that all the elements are covered. So for that, we need to introduce the grid stride loops. Okay, so here, instead of this if condition, what you have to do is, you have to apply the for loop. Okay, so you put for, okay, int id equal to I, okay, id less than n, id plus plus. So here, instead of id plus plus, what I have to do is id equal to id plus stride. I hope you understand why I made id plus stride. So id plus stride is making the thread with the given id I to work on the data items in a stride fashion, right? So the zeroth thread will be accessing the elements in the corresponding stride. Let's write the formula to find the stride value. So let us say stride, int stride is equal to, as the formula was given by Anjali, that is dim dot x into block dim dot x. So this will give me the total number of threads that are launched by the given launch parameters in the CUDA kernel, right? So this will give the value of stride. Now with this, I will be able to access the all of the elements. So it is saying all the elements are doubled, it is saying false. So there is something that is missing. Let's find it out. So can you guess what is the mistake here. The mistake is here we are writing I, but what we should write is ID. Is it or not? So we should write here ID. It was a silly mistake. It was not intended. Okay. Now if I again check, it will return me true. Okay. Is it clear to everyone? Am I audible? Am I audible? Okay. Fine. Thank you. Now let us say that I remove this for stride value. I remove this stride thing. So if I say that I'm not going to apply this stride strategy, what will happen is my elements will be partially doubled, not complete. Only 8192 elements will be doubled and no one will access the remaining elements. Okay, so if I run this, I'll okay ID here I have to put I. So if I run this code again, you can see that I'll get false. Why false? Because I'm not accessing, or you can say I have not allotted all the data elements to the threads. So because my number of threads are less than number of data items, right? So if my data elements are more than total number of threads that are launched, I have to use this strategy of grid stride loops, wherein stride value is calculated grid dimension into block dimension. Grid dimension is number of blocks in a grid. Block dimension is number of threads in a block. Okay, so this is how you calculate. Now next part is error handling. We all know that error handling is very crucial part in writing the efficient code, and error handling lets us know what has gone wrong if we are not getting the correct results. If compilation is successful but still we are not getting correct results, so there is a high chance that the kernel launch is not done properly, or there is some issue in the kernel logic. Okay, so in order to find that particular error messages, CUDA has introduced the new variable type, that is CUDA error underscore t. This type, or you can say this variable will tell us the status of the kernel, whether it has executed successfully or not. Okay, so basically any CUDA runtime function or CUDA runtime errors are caught by the or you can say can be shown with the help of this particular variable. So any CUDA function, you can check whether the memory unified memory allocation was successful or not with the help of this particular error handling mechanism. So here what we are doing is, here we are declaring this variable CUDA malloc managed will return us the CUDA success if the memory management is successful. Otherwise it won't return CUDA success. Okay, so CUDA success is you can say is a variable, it is a value which is already and is provided by the CUDA. Okay, so if this call is successful, you will get CUDA success value inside ERR variable, and we are checking the same. Is it equal? If it is not, that means there is some mistake, and that's what we are trying to print. So that error message we print with the help of CUDA get error string, and we pass the variable inside this. So this is how you handle the errors. So errors can be of any type. So there can be the error while launching the kernel. So let us say we are passing by mistake negative value to the threads per block. We all know that threads per block is a number and it should not be zero. Sorry, it should not be less than zero. Okay. So if you are passing the launching the kernel with negative number, so there is a launching configuration mistake which will be caught by this um, which will be caught by this variable. Okay. One more thing is CUDA kernel launch does not return anything, but this kernel launch will not return anything. But you can get the launch error by executing CUDA get last error statement. So after kernel launch, you can get what has gone wrong by putting this CUDA get last error statement just after the kernel launch. So if you launch the kernel, have this line of code to check for any errors in your kernel launch. So if there is any error, you will have that message getting printed. Okay. So let's try to any questions so far? Any questions? Or shall we proceed? Any questions? Please let me know. Am I audible? Hello? Am I audible? Okay, fine, fine. Thank you. So we will have this. So currently this will compile and print the elements which are not successfully doubled. So there is some mistake, okay, in the code. So what we have to do is we have to find out the error that is being there in the kernel launch or in a kernel, which is making it unsuccessful. So I am not changing anything. I am trying to run the code, run this cell directly. So it is returning me false. Okay, all elements were doubled, so it is returning me as false. So let us check for the let us add the error handling mechanism in our code and see. Okay, so before kernel launch, let us try to now first of all, can you tell me is there any mistake in this kernel code quickly? Here IDX is calculating the thread ID. It is correct. Stride, this formula is also correct. I think there is this mistake. I is less than n plus stride, right? So this you can remove. Okay. Before adding any error messages, let us try to see if there any logical mistake. Okay. So that was okay. Now let's try to rerun the code. It will again display the false message. Okay. So for this, there is CUDA error handling mechanism with us. So let us try to initialize the variable first. So we all know it is CUDA error underscore t. Okay. Now here, after the kernel launch, we have to find the value. So that is CUDA get last error. Okay. So if you look at this, we are looking at, right? So now then we check this condition. I simply copy paste here. So here what I am doing is, I feel that the code is correct, but still I am getting the wrong results. I will have getting print code. So this way you can print the error message onto the console. Okay. Now once this is done, let us save this code and rerun the program. If you look at, you will get this printed with invalid configuration argument. That means what? Our configuration is configuration argument. That means what? Number of blocks and number of threads. This is wrong here. Now the thing is, number of first thing is here it should be number of blocks, threads per block. It is also correct, but still it is giving me the error. Is the limitation of our GPU. The limitation is I cannot more than 10 in my block time. So the thing is, my launching configuration is wrong. So threads per block should not be more than 1024. Here the number of threads per block is given as 2048, which is wrong. So we have to reconfigure as 1024 or less than 1024. You can have it 256. Now after this modification, let us recompile the code. If you look at, it will return us the true value. Are you getting my point? Are you getting my point? So here you can have any value which is 104. So you can actually have 256 also. The reason is we are using the stride based strategy. So I am not bothered about how many threads are launched, whether the launched threads are less than the actual required threads, because I am dealing with the threads stride based strategy. So still it will give me the value as true. Okay. So this is all about the first unit that we have learned so far. We will quickly see the second chapter, and then we can jump to the direct assignment directly, because third unit is all about the visualization, which you can also study later on. As part of the requirement of this certification, the first two units are more necessary, and that too first unit is much more required to be known. So if any doubt so far, please let me know. Any questions so far? Any questions? Any questions? Please let me know. No questions? Fine. So let's move on to the final exercise. Uh, Everyone is following me on the WebEx, right? Please open the WebEx. Please follow me on my screen.
Yes, sir.
Okay. So we will have this final exercise for this first unit concept that we have learned so far. Okay. Do we will follow the instructions that are there in this notebook. So first we will open this program. What they have asked is it contains the functions. It contains functioning CPU only vector addition application. So we have a vector addition application which is a CPU only code. What we have to do is we have to accelerate this add vectors into function. So add vectors into function, we have to convert it into the CUDA kernel on the GPU so that it will work on the GPU. Consider the following need to okay, following should be happening. So the arguments to the add vectors into so that the okay, we have to convert this add vector into the CUDA kernel. So the 11th number line, what should be done? We have to put the global variable here, sorry, global keyword here, right? So now this is making it as a CUDA kernel. Next thing is choose and utilize working execution configuration so that it launches a CUDA kernel. So before going, remove this for loop so that we have to write this code for per thread, and we know which thread should not. So this for loop should not be there for elements, but it should be for the stride. Is it or not? So this we have to modify. So here, first thing that we have to do is we have to find the ID of my thread. So that you can get it with the help of int ID is equal to thread ID x dot x plus block ID x dot x into block dim dot x, right? So this is done. Next thing is I have to find the value of stride. So int stride is equal to, what is the formula? That is block dim dot x, right? Now we have to modify this for loop. Instead of I plus plus, what I have to do is I equal to I plus stride. Now my kernel is okay, right? Now my kernel is correct. Now let us change the configuration. Now can you tell me what is wrong here? In line number 46 to 48, can anyone tell me, is it correct way to launch or to allocate the memory to the variable? If not, what way we should allocate? Please reply quickly. I'm waiting for your replies. Very good. So we have to use the CUDA malloc managed, right? So CUDA malloc managed. Inside this we have to use ampersand a, sorry, comma size, right? Same is the case for B and C. Okay. So for B and this is for C. Okay. Now this is done. Next thing is Now next thing is I have to launch this add vectors into with the help of CUDA launching parameters, right? So here I have to launch the blocks, comma, threads. Now I have to define the value of threads to be launched and value of blocks to be launched. Can you tell me? Let us say my thread value is int thread is equal to 256, right? Can you tell me what should be my blocks value? Can you reply in chat? What should be my blocks value? I am having number of elements as n. I am having number of threads per block as 256, or let us say, let us write it properly, threads per block, and here number of block. Here threads per block. Let us say I want to launch threads per block. I'm having n number of elements blocks I need. So we know the formula, right? Someone has replied. Am I audible? Am I audible? Hello? Okay. Okay. So can you tell me what should be the number of blocks? The formula that we have seen, right? So n by 256 or n plus, yeah, good. So Ayush, n by 256 won't give me the exact amount because it is going to give me if it is okay if it is divisible by 256 perfectly, but if it is not, the formula should be n plus threads per block actually n by 256 should also work, minus 1 divided by threads per block, right? So now we have correct threads per block and number of blocks. After this, we have to add the CUDA device synchronize statement. Okay. Now, as A, B, and C are allocated with the help of CUDA malloc managed, we have to use the CUDA free function, not free. So you write CUDA free. Okay. Now I have made the required changes. Let me check if my code is correctly working or not. Okay. So there is some spelling mistake. Fine. Line number 13 and 14. What is the, let me check. Okay, again a silly mistake. So here, what we have to do is we have to initialize this I with ID not 0, because we are referring here for a particular thread, right? So we should start with that particular thread ID and go on incrementing it with the stride value. So that was a simple change that need to be done. I hope you are getting. Okay. So what the success asset, all the values added correctly. So this is how the first unit. Any questions we can discuss, or we will start with the second unit. Any questions? Any questions? Please let me know so far. Any questions? Fine. So thank you. So we will, so this is, there is advanced contents that you can experiment when you have time after this workshop. But as for today's workshop, this much is sufficient, and we can move ahead with the second unit. So everyone is requested to close this notebook and stop this task. Okay, you have to stop the task. Once you are done, you can click on the second unit, that is synchronous streaming and visual profiling. Synchronous streaming. Sorry, not synchronous streaming. It must be managed applications with CUDA. That is the second unit. So that let's of 10 minutes. We'll be back at Is my screen visible? Hello. Okay, thank you. So now we are at the start of second unit. In this unit, uh, we will be using the NSYS tool to optimize our code, check whether what is happening inside the GPU, what are the resources being executed, and where we can optimize our code. Uh, Next, we will look at how the streaming processors are arranged inside the GPU. What is the unified memory? What is the use of asynchronous memory prefetching? So these concepts we will be looking at, and for because of the time limit, we will have a fast look because we already have spent lot of time in understanding the basic concepts uh, in understanding the CUDA, right? So I hope these second unit you will be very familiar. We are now familiar with the CUDA concept, so we can move ahead fastly with the second unit. Now, with this in mind that we have just solved the previous exercise, that is vector add.cu. So with this file, we can actually check the different CUDA API statistics, CUDA kernel statistic, memory operation statistics, which is being happening when we are executing this code. Okay, so let us recompile the code again. Okay, the previous code that we have. Okay, and it is sending the message that okay, all values are calculated correctly. Now NSYS is the NVIDIA Insight tool which actually creates the profile for your CUDA kernel and gives you the insight about what are the different execution uh, parameters that are there in your while execution of your program. Let us say how much memory is consumed, how much time is taken, how much time is consumed in synchronizing the kernel, in launching the kernel, and so on. Uh, how many page faults are there, and so on. How many memory transfers are there. So if we execute this, it will generate a report which will give you the idea of different things. So if you look at, it is giving us the kernel statistics that okay, total time in nanoseconds. It is giving us the time in the nanoseconds, that okay, this much time in nanosecond is taken by the particular CUDA kernel, that is add vectors into kernel. Okay, now someone have asked me that if we are using CUDA malloc managed, is there any need of memory transfer? So yes, there is no need to mention it explicitly, but CUDA API is doing it implicitly, and here is the evidence, right? So if you look at, there are two operations happening. One is CUDA unified memory memcopy host to device. So the array is transferred from host to device, the calculation is done, and then again the result is copied back from device to host. So these two memory operations are there in the code. I hope you can understand, right? So this is in terms of time, this is in terms of bytes, kilobytes. So one and the same thing, just unit is different. Okay, so now our task is to optimize this code. As of now, it is taking just focus on the time. Okay, we will just note down this time. So the total time to execute the CUDA kernel is this much nanoseconds. So let me copy this. We will just wait. Okay, so this is the time in nanosecond for the first version of our CUDA kernel. Even though it is executed by the GPU, but still we can reduce the time which is being required. So let us try to modify the code such that it will execute in less amount of time. Am I audible? Am I audible? Hello? Can you quickly reply? Okay, fine. So if you look at the code is correct, the device code is also correct, launching is also correct, everything is correct. But the thing that we can change is this code is launching only one thread. So it is as good as the sequential code. Is it or not? We can change this to launch many number of threads. Is it or not? So let us say I will try to launch 10 threads per block in a single block. So what is we must see some change in the hello. Am I audible? Hello. So with this change, let us recompile the code. What we have done is we have changed from 11 to 110. Okay. So yeah, we got the success message, but this time, if you look at the time taken is reduced. So I'll copy this time here. So with more number of threads, our kernel is taking less time. I hope you are convinced. Now let us again increase the number of blocks, or you can say number of threads. Let us launch 256 threads in a single block. Again, if you recompile the code, you will get the success message, but this time with the reduced amount of time. If you look at the time is reduced. So I'll again copy paste this time here. So the time is reduced. Is it or not? So why this reduction of time is happening? Because we are optimizing our code such that we are launching more and more number of threads. But this won't go beyond 1024, right? So let us say that I want to launch 256 threads in 10 blocks. So 10 blocks, 256 threads. So those many threads I am launching. So I must see the more optimization in my execution. So let us recalculate the time that is required, and if you can look at the time required is much lesser as compared to previous runs. I hope you can understand. So for those who are confused what we are doing here, we are just simply compiled the code in this case, compile and run. Then based on the profile that is being created by this nsys command, it ships with the NVIDIA CUDA API. Okay, so with the NVIDIA CUDA API, there is nsys, which actually is used for profiling your kernel so that you can do the more and more optimizations. So this gives us more visualization uh, towards the kernel time that is required, so that we can optimize our code, so that our application takes less and less amount of time. A small change can have lot of difference in case of parallel computing. So you can change the parameters by analyzing the profile that is being shown here. Okay, So this is how you can profile the code. Now, basically, this thing that we are launching, we are unaware of the number of streaming processors. We are just randomly, up to now we have just randomly taken the number of blocks, right? But if you think logically, if we launch the number of blocks which are in multiple of number of streaming processors, so each streaming processor will get equal amount of block to process. So so that we can use the available compute capability at its fullest strength. Is it or not? So it is therefore advised to check for the available number of streaming processors that are available with us and use the number of blocks which are in multiple of streaming processors. So two things that are to be taken care of. One thing is your number of threads per block should be multiple of 32. Number of blocks in a grid should be multiple of number of streaming multiprocessors with you. So if you take care of these two parts, you are going to launch the kernel with the efficient number of threads. Okay, so you take care of these two things. Now, how to find the number of streaming processor? Before going ahead, there is a small presentation. We will have a look at that. Am I audible? Hello? Please reply. Am I audible? Okay, fine. We know that a GPU contains lot many cores, and those cores are nothing but the streaming multiprocessors, or you can call it as the SMs. So GPU consists of many such SMs. If you launch this kernel in such a way that the launching parameters are 24, 4, what does it mean? There are 24 blocks and each block contains the 4 threads. Now in this case, there are 24 blocks and 24 SMs. So each SM will be working on one block at a time. Is it or not? So, here the number of SMs are 16, right? So we have these 8 blocks unassigned. The 16 SM will be allocated the first 16 blocks. What about the remaining what about the remaining 8 blocks? They will also be assigned in the next iteration. But what about the remaining SMs? They are sitting idle. So the resources are not utilized properly. We might have done more amount of computations if we have launched more amount of blocks. Okay, so there should be the mechanism in such a way that we should launch the number of blocks which are multiple of number of SMs in our kernel launch. Okay, so that we promote the full optimization of our kernels. So this is why there is a concept of uh, streaming processor count. I hope this is clear to everyone. Any question? Any question? Is it clear that why we need number of blocks which are multiple of streaming processors? It is clear, right? So there are two things to be taken care of. First thing is number of threads should be multiple of 32, that is warp size. Number of blocks should be multiple of streaming processors. So what is warp? Warp is collection of 32 threads in a block. So we know that collection of threads is a block. Now within a block, threads are again grouped into the warp. okay, and they perform the work in a lockstep. So it is advised that you schedule the threads per block which are multiple of warp size, which is 32. Okay, so this is one thing that is to be taken care of. So every time you choose the number of threads per block, it should be multiple of 32. Next thing, every time you choose the number of blocks, it should be multiple of streaming multiprocessors. Now, how to get the streaming multiprocessor count? So in CUDA, you have this functionality that is, it will give you the ID of the device. So normally in our laptops that we are having, only a single GPU device is there. But if your system consists of more than one device or more than one GPUs, then that time the device ID might be having more than one value, that is 0 and 1. Okay, if two devices are there. So normally, let us assume that a device ID is 0 only. So how to get that? You can have this int device ID and then get CUDA get device. This will return us the device ID of the current GPU. On this device ID, what is the particular count of streaming processor that we want to find? So that is that you can get with the help of CUDA device properties function. Okay, am I audible? Am I audible? Hello? Okay,
Yes, sir.
thank you. Okay, so let's try and query the current GPU that we are having, that how many streaming multiprocessors are available with us. So this program, please don't open your notebook, just follow me. Okay, so in this program, we are not calling any kernel, but we are just querying the GPU. Okay, so here if you see this, we have this int device ID, then you call this particular function and pass this device ID. So now this device ID will have the information about the current GPU. What is the ID of the current GPU, right? Now next is, I want to get the information about the compute capability measure, compute capability minor, multiprocessor count. So these thing and what is the warp size of my current GPU? So this information I don't know as of now as a programmer, right? So I want to fetch these values, these properties, these attributes of my GPU. So to get that, I create the variable of CUDA device property type. So you write CUDA device. Okay, and then query CUDA get device properties, pass the address of prop variable that you have created and the device ID. Once you get that, you are now having all the properties of the GPU that is available to you. To fetch the measure, you can call prop.measure. Here you can call prop.minor. Okay, here you can call prop.multiprocessor count. So these are all predefined variables. Okay, so I'm not writing any logic here. I'm just accessing the properties from this prop structure. Okay, so these are the different attributes available to me. So prop dot warp size. So these are the attributes that I have got. Now I have saved the code and I will try to run this and I'll get the properties of my GPU. So with this, I am getting number of SMs in my GPU as 40. So can you tell me, is this launching is correct? I am trying to launch, sorry. Earlier we have launched the CUDA kernel with the 10 blocks. Is 10 multiple of 40? If you look at the 10 is not multiple of 40, 10 is much lesser than 40. So ideally we should launch the blocks which are 40 or multiple of 40. Is it or not? So therefore, if we modify our code in such a way that we launch the number of blocks which are multiple of 40, we launch the threads which are multiple of warp size, that is 32, we will get the optimized version of our code. Okay, so let us try to remodify, let us try to change this code with this simple modification. Okay, so are you able to follow me? Am I audible? Hello? Okay, fine. So inside the main function, what we will do is I have used 10. Instead of 10, we have to launch the total blocks which are multiple of number of SMs in our GPU, right? So that we can get with the help of, I'll directly copy paste. We won't waste time. So here I am not interested to know major and minor. Okay. So now multiprocessor count is the count of multiprocessor, which is 40 that we will get. Is it or not? So this I have to make sure that it should be number of blocks should be multiple of multiprocessor count. So here instead of 10, what I will do is I will allocate as many blocks as necessary for me. So let us say threads per block plus n minus 1 divided by threads per block. Okay, so this is the thing. Now here you check if what you have to check is my number of blocks are multiple of number of SMs. So you check if number of blocks mod multiprocessor count is not equal to 0. If it is not equal to 0 means what? It is not multiple, right? So you make it multiple. So you make number of blocks is equal to number of blocks divided by multiprocessor count plus 1 into multiprocessor count. So this statement will make sure that your number of blocks are adjusted such that it is multiple of multiprocessor count. Okay, so with this change, we should be getting the optimized output. So let us check whether, okay, 77 line number. There is some mistake. Let me check. Okay, we have to fine. There is some silly mistake. Let me correct it. Am I audible? Fine. So now our program is correct. Let me profile my code. We should get the less amount of time. If you look at, we have got more optimization now. So this is with the, even though you can't see more result, but yeah, the code is optimized somehow. Fine. So this is how you can work on and optimize the code with the help of ANSYS. Any questions so far? So can you repeat where you can change the code? Can you please unmute yourself, Priyanka?
Yes,
Hello?
sir. I want to know about code where
Yeah.
if number of block divide by multiple processor count.
Huh. This this one, this one, this one, right?
Yeah, yeah, sir. Yeah.
Hello?
Yes, sir. Yes.
Yeah. We are writing only to, you can say only to say that my number of blocks should be multiple of multiprocessor count. Otherwise, what will happen is I am having 40 multiprocessors, but earlier I was launching only 10 blocks. So one more thing is that each block, a complete block, is assigned to a single SM. It won't happen that a block is divided into two different SMs. No, each block, or you can say each SM will execute complete block, not partial. Are you getting? So if I am having 40 SMs, why would I launch the blocks which are less than 40? I will think of launching 40 or more than 40 blocks, right? Because I am having more compute capability. I am having more number of resources with me. So I should utilize them. So instead of launching only 10 blocks, I will think of launching the blocks which are multiple of number of multiprocessors that I am having. That's what this line of code is doing here. And this is a simple logic to check if it is multiple. So if mod is not 0, that means what? I am not it is not completely divisible by the multiprocessor count. So simply I am going to have this being a factor of multiprocessor count. So just to cross check, let us have a print statement here. Okay, so let me print the value before allocating. Let me print the number of blocks here. Okay, so number of blocks. This is before adjustment. Okay, now after adjustment, let us say number of blocks after this calculation is not multiple of 40 that we are printing here. So our code will adjust it, the number of block count, to be multiple of 40. So again, let us print this line. Okay, and if you rerun the code, you can find the we will ignore these warnings. If you look at the first number is the number of blocks which is being calculated with the formula that we have discussed before lunch, right? So with this formula we got the number of blocks and we printed, which is this one, but it is not multiple of 40. So this number is adjusted in a way that it becomes multiple of 40. It is not multiple of 40, so therefore we are making it multiple of 40 with this formula. So we are again inside this if condition. This condition becomes true, so we are here and we are printing the modified number of blocks again. So this is multiple of 40, therefore we get the optimized result. I hope the point is clear. Why the size should be multiple of 32? See, the 32 is not a magic number, it's a warp size. So basically what happens in GPU when you launch the threads are launched in the grid of blocks of threads. So inside the block, again you have group of threads. It is known as warp. So within a block, the threads are executed in a group, and that group is nothing but a warp. That warp size is 32 in our case that we have queried in the last program itself, right? So that if you look at here is the warp size is 32. So the reason why the warp size reason why the number of threads should be multiple of warp size is to efficiently execute within a block. Because if you don't put the warp size which is multiple of 32, what will happen is, let us say you choose the number of threads as 34. So what will happen? It will form two groups. One group is of 32 threads, another group is of only 2 threads. Because within a block, even though we are able to allocate 1024 threads at max, but 34 is not multiple of 32. So 34 threads if you launch, those threads will be launched in a block, will be executing in a kernel in a two groups. One group is of 32 threads, another group will be of 2 threads. So there will be the you are not, again you are not using the complete compute capability of your GPU. Even though the second block can execute 32 threads, but you are executing only 2 threads in that particular warp. I hope it is clear to you. So it is only to ensure that you are using the GPU at its full strength. It does not give you any error or any wrong results. It is just for the optimization purpose. Is it clear, sir? Uh, yeah, thank you. So that was the discussion we had. Now let us come back to the unified memory. Uh, in previous some of the programs we are working on with on the data and we have seen that we have allocated the memory onto the unified memory with the help of CUDA malloc managed, but we are still not that much comfortable with it. The reason is we just know that okay, this is the way you initialize the data, but we are not confident enough what is going to happen next, like how the data is being transmitted from here to there and there to here. Someone have asked, is the data transfer still needed? So the answer to this is yes, data transfer is needed and it is done automatically. Okay, so let us see it in the presentation briefly. This we have seen. Oh, just wait. Okay, fine. So when you allocate the memory with the help of CUDA malloc managed, the memory is not available initially to the CPU or GPU. It is actually some other part of the memory. And when you want to access the memory, whether it is a CPU or GPU, the page fault will occur and that portion of the memory is brought to the particular resource, whether it is CPU or GPU. Okay, so when you try to access the data which is on the unified memory, the migration happens from unified memory to the CPU or from unified memory to the GPU. For the first use, what happens is the data is migrated, but once it is migrated to the particular resource, next when it is required by the another resource, the data has to be moved from one resource to the other resource. Internally it happens because the mechanism, we know that when the page fault occurs, it demands that for that particular data, and that page containing that data is loaded into the memory and you go on working with the data. We all know about this, right? So now let us try to look at the page faults that are being occurring in this particular code, which is that 01 page faults.cu, which contains the host functions, and it is trying to it is having a vector of 2 to the power 24 elements. Okay, and what we have to do is we are going to see all these different 4 questions. Okay, so rather than going ahead with this and modifying, we'll directly click on the solution and discuss. Okay, so is there any evidence of migration and or page faulting when unified memory is accessed only by the CPU? So when we access the memory only by the CPU, so only by the CPU means what? I am not going to call the GPU kernel. I am calling here only the CPU kernel. Can you see any GPU kernel launch here? No. So if there is no GPU kernel launch, means GPU is, or you can say only CPU function is called. Okay, even though GPU function is defined, but it is not invoked. So any guesses here? So what we'll do is we'll copy this. Okay. So the first question is, what happens when unified memory is accessed only by the GPU? Is only accessed by the GPU. So let us say we want to call this function, that is device kernel. So we are trying to access only the GPU. Okay. Let us launch one only. We will make it very simple just for demonstration purpose. Okay, and it is passing a and n as the parameters. So a comma n. Okay, so here and after this we will use CUDA device synchronize. So if you use this CUDA device synchronize and this call, it will make sure that CPU will wait for execution of GPU, right? So let us run the profiler. First we will run the code. Okay. It is not displaying anything because we are not printing anything in the program. Okay. So let's profile the code. If you look at the kernel launch has happened and it has taken this much amount of time. But can you see any memory operations occurring here? Any memory operations like we have seen host to device or device to host earlier? Nothing has happened, right? Similarly, if you change this code to just call the CPU function, if we call only the, what happens if unified memory is accessed only by the CPU? So what is the name of CPU function? That is host function. So let us call this host function here. I have commented the GPU function call. So a comma n. Again, so now it is compiled successfully. Let us run. Again, it won't show any data transfer, right? Because for the first access, the data is not shifted. But the moment you use both the things, let us say I am trying to use this and this all together. So first I will call the GPU function, then I'll call the CPU function, and then try to run this code again. So you will see the data migration. So in this case, you will see one data migration that is being happening, that is from device to host. If you look at, there is memory operation. Are you following me? Hello? Am I audible? Am I audible? Hello? Am I audible? Okay, fine. Aditya sir, let us discuss later on. There is a less amount of time remaining. We will discuss. We will have this discussion later on. Okay, fine. So I hope the point is clear. So first we are done on the device. So next I need this A to be used at the CPU end. So from device to host, there is a copy. Is it or not? So, and how much operations are being done? If you look at the operations that are done is 768. So 768 memory copy has been done, and by size minimum 4 bytes and maximum 1020 kilobytes are transferred. So now can we reduce this? So the answer to this is yes. We can do this with the help of memory prefetch. Memory prefetch is a technique in which you know that the data is in a sequential manner, and uh, you can actually not means the data is not scattered and it is all available in a memory in a contiguous fashion, and you know that the data is required later on in the computation. So what you do is, in that case, you prefetch the data. So the data prefetching is kind of asynchronous. It will go on, so it will prefetch the array A, so that the page faulting is reduced. So in this case, total 768 memory operations are done. And we all know that memory operations are costly. They consume lot of time. So our goal is to reduce this count. Okay. So for that, there is a concept called as the memory prefetch. Okay. That is how we will use this asynchronous memory prefetching, which is a powerful technique for reducing the overhead of the page faulting. Here you might have observed that total uh, 768 memory operations are done, and this much amount of data is transmitted, total data is transmitted. Okay, so in order to reduce this operation, we need to prefetch the data to the CPU from the GPU, and this is done with the help of prefetching, asynchronous prefetching. Okay, so for prefetching, we should know what is the device that is we are working on. We Once we get the device ID, okay, then we use this function called as CUDA mem prefetch async. So CUDA mem prefetch async, what it will do is it will prefetch the data from where to where. So that is being decided by this device ID. So this device ID is nothing but whether it is to be prefetched to which GPU, or if you want to prefetch the data to the CPU, this is the thing that you have to mention, that is CUDA CPU device ID. Okay, so CUDA CPU device ID is the thing that you have to mention if you want to prefetch the data to the CPU. Okay, so this first statement prefetches the data to the GPU. The second statement prefetches the data to the GPU. So let us try to optimize the code again so that the memory operations are reduced. Okay, just wait. I got one call. Just wait. I'll be back. Just wait. Am I audible? Am I audible? Hello. Okay. Right. Just 15 more minutes, then we will have the final exercise. Okay. Just 15 more minutes. So our goal is to reduce the memory operations, and that can be done with the help of CUDA mem prefetch operation, right? So let us try to modify our code, and so in this code, this is our vector. Sorry, this is our GPU kernel. Okay, it is written correctly. We are now have to focus on the kernel launch. Okay, so if you look at in this particular kernel launch, first this code is correct. It is working correctly, right? Because this is what we have modified. We have optimized the code such that we are launching the uh, threads per block which are multiple of 32. We are launching the blocks which are multiple of number of multiprocessors. Okay, now this is done. Now let us try to see where is the data prefetch that we need to perform. So one thing is we can perform the data prefetch here before launch of the kernel, because the data is initialized at the CPU end first, right? If you look at, the data is initialized at the CPU side, so there is no need, and after initialization we are launching the kernel. So from CPU to GPU there is a need of data prefetch, right? So that data prefetch code we have to write just before the kernel launch happens. That is here. Okay, so let's copy this thing. Okay, now pointer to some data. Here what I should write? Pointer to some data. What is the pointer? What is the data? The data is nothing but A. Is it or not? I'm working on A, right? I'm working on A first, then again I will be working on B, because I am working on 3 vectors, right? So data prefetch should be happening for all of these devices. Then we are having C. Okay. Now with this change, can you tell me, is there any CUDA mem prefetch required again? Can you reply? See, before launch of kernel, we have prefetched the data to the kernel, right? Now again, after computation, we need another data prefetch, but that should be to the CPU end. Is it or not? Because here we are calling check elements are, which is a CPU function. Now because we have worked on the GPU, the data is now residing at the GPU end. We have to prefetch the data from GPU to the CPU. So again we have to change this code. We have to add this second line here. So before call to the CPU function after GPU kernel launch, only the change that you have to make is, now see what type of data you are accessing in the CPU after GPU launch. Only C array, right? So you just prefetch the C array. You don't have to prefetch A and B, because C array is the one which stores the result, and we are interested in that only in the CPU function call. So we are prefetching that only. Now once that is done, now this is our most optimized code that we could write. Let us try to see how much time it takes now. Let us ignore these warnings. So if you look at the time taken is much lesser as compared to previous kernel launches. Can you see the difference? This time is much less than the previous optimization that we had. Are you able to see the difference? Hello? Are you are you
Yes, sir.
getting the point? Okay, fine. One more thing is uh, we want to see the operations. So earlier, before prefetching, the operations were around 700, right? Now these operations are reduced. So also the amount of data, if you look at in KB, the minimum and maximum is same. What does it mean? It means that prefetching works in terms of chunks of data. The complete chunk of data is prefetched to the particular resource for processing, so that we get the optimized code, and the memory operation, or you can say memory uh, transfer time or overhead is reduced. But this advantage is only because we are dealing with the data which is stored in a contiguous memory locations. This prefetching won't work if you are dealing with the scattered data. Okay, so the condition for working with the prefetching thing is your data should be in a sequential manner. It should no, I mean it should be in a contiguous memory locations. Okay, so that's all for the second unit. I hope uh, you got the uh, concepts up to now, and those who are still not getting the things, don't worry, you have this self-explanatory lab available with you all the time. You can come and see this part again and again until you get the things. Now it's time to have the final assessment things. Okay, so with the knowledge that we have acquired so far, we are now in a position to solve the final assignment, which will give you the certification of this course. So all are ready, or you need a 5 minute break? Just let me know. Or should we directly start? What I'll do is I'll discuss the final assignment with you. Okay, and we will work together to optimize the code. So please reply here. Uh, shall we continue or have a break for 5 minutes? Hello, am I audible?
Yes, sir. Continue, please.
Okay, fine, fine. We'll continue. So everyone now should open the third unit, that is asynchronous streaming and visual profiling for accelerated applications. So please open this third unit. Everyone, please open this third unit, that is asynchronous streaming and visual profiling for accelerated application. You click on the start button. If you get such type of message, you click on the stop and again restart. One thing I want to mention here is that for certification purpose, whatever the knowledge required is covered up to now. The third unit deals with some additional knowledge which is not required to solve the assignment. So I feel that you will be learning this by your own, the additional concepts. I have left some part for you to be done by your own things. Okay, but still you are now able to you will be able to solve the final assessment with the knowledge that we have learned so far. Okay, so rather than discussing the additional parts which can be covered by your own, we will directly jump to the final assignment. Okay, so just once you get these three buttons, you click on the launch button. Click here, click on the launch, and this is very crucial part, so please be responsive. Okay, so is the third unit Jupyter Notebook is open at your end? Please reply. We will be solving the assignment together. Okay, fine. So first what we will do is we will see the problem statement, see the code, and discuss what are the things that we can do for optimizing the code. Okay, and then I will optimize and I'll let you know where the optimizations are to be done. Okay, and you also do at your end, try to optimize the code, and once that is done, if we get the correct answer and assessment is successful, I'll tell you the process to generate the certificate in this course. Okay, so just 10 more minutes. So once you are on this page, go to the scroll down. So I am skipping this as part of your own homework. So you have to do this later on after the certification. Okay. So this is just additional part for the people who want to do more and more profiling. Okay. So up to now, whatever we have learned is sufficient for certification. So that's why I'm directly jumping onto the certification part. So everyone, have you got this final exercise? Accelerate, optimize, N body simulator.
Sir,
If you don't find it, hello,
sir, my Jupyter
hello,
notebook password.
what, ma'am?
My Jupyter notebook
Hello,
password or token.
you are not audible clearly, ma'am. Hello, can you type? Am I audible? Okay. So Jupyter Notebook, ask password or token. You do one thing, your session might have gone, so you can revisit that NVIDIA course page. You come here onto the course NVIDIA, okay, and you re-log in again. From here, you can log out, again re-log in. After re-login, you come to the My Learning, and then you click here. Then you will be able to access your notebook again. This might be because of the network issues or your session issues. Okay, fine. So once you are here, I will suggest that you search for you type Control F and you search for N body. Okay, and After summary, there is final exercise, which says accelerate and optimize an n-body simulator. So that this is the exercise that we have to finish in order to get the certification. Everyone is here? Everyone is up to here? Everyone got this page? Everyone? Okay, fine. So now please be on my screen. Please be on the WebEx screen. So basically, we have to accelerate this n-body simulator, which don't go into the technicalities. We won't go into the technicalities, what it is do, what is it is used for, and all. We will just focus on the computational part, which is required for us to accelerate. Okay. So what we will do is we will open this n-body simulator.cu. Okay. Now here we have what they are saying is it is CPU only form. So this is a CPU only code that is being provided to us. This application takes about 5 seconds to run on 4096 particles and 20 minutes to these many particles. So what we have to do, so there is a guideline for us to do. What we have to do, especially for your first refactors, the logic, the application, the body force function in particular can and should remain largely unchanged. So body force function should not be changed. So don't do anything to this function. Okay. We have to focus on accelerating as many as possible. So the logic should be unchanged. We don't have to change the logic. So you just change this function in a way to execute it onto the GPU, but the logic should not be changed. Logic means the computation logic should not be changed. So our goal is to make this body force as a GPU kernel. Next thing, the code base contains for loop inside the main for integrating the inter-body forces calculated by body force. Okay. So we have to integrate this, and after it runs, it needs to complete before next call to the body force. Okay. So there is you have to use the profile driven iterative approach such that you track the progress of the changes that you have done. Okay. You have to add the error handling. So it is not compulsory, okay, to add or not. It is on you. But if you wish to, you can add the error handling code. Okay. Now let us discuss this. Now if you look at, we can see we have to change this body force function into the GPU part, right? So for that, first thing that we have to do is we have to put underscore underscore global underscore underscore. Okay. So this will make this body force as the CUDA kernel. Okay. Next thing that you have to consider is this for loop. This for loop is nothing but, you can think of it as per thread activity. So you can simply ignore this for loop, is it or not? So instead of ignoring, what we will do is we will convert this for loop into the stride. Okay. So what we will do, we will calculate the thread ID. So int ID is equal to threads per block. Sorry. Thread ID x dot x plus block ID x dot x into blockdim.x. So this you have to do. Then once the ID is calculated, you calculate the stride int stride is equal to griddim.x into blockdim.x. Now inside this for loop, what you have to do is int I equal to id, I less than n, I equal to I plus stride. I hope you are able to follow me. Am I audible? Am I audible? Hello? Am I audible?
Yes, sir.
Okay, fine. I will request everyone to first look at the screen, then you can work on the code at your end.
Sir.
Now, if we look at this part, should be kept outside this for loop. So I'm just putting it here. Okay. One more thing that we have to change is p of I dot x, these things, right? So instead of p of I, we can have this p of id. Here also p of id, p of id. The reason is we are inside this particular stride loop, we are accessing the elements such a way that each thread will have more than one number of elements to be processed. Is it or not? So therefore we are changing this in such a way that we are making it p of id dot x, p of id dot y instead of p of I, because id represents, and in our iteration also we are specifically focusing on that particular thread value. Okay, so this is the change that we done here. Rest of the things you can be kept unchanged. Okay. Now next, you can next thing is you can have this now this function will go up to here. Okay, fine. So this call is given. Now next thing is this part. Okay, so this part inside the main, we have the n bodies variable, right? And this buff need to be allocated with the help of CUDA malloc managed. Is it or not? So you make sure that it is allocated with the help of CUDA malloc managed. I'm doing this because you will be able to understand. Otherwise, I would directly have shown the solution to you. But because we are working clear what we are doing here. Okay, so this is done. Okay, now rest of the code will remain unchanged. Okay, now next thing is, here is the call to the function which we have converted it as a GPU code, right? So here we know that our let us assume that it is, we want to launch the CUDA kernel with the 256 threads per block, and sorry, to the number of blocks as multiple of 40 we want, right? So let us say 40 comma 256. I am directly putting the values, them as we have done earlier. Okay, so this is to be done. Then this will give the call to the uh, mm, kernel. This will launch the kernel. Now if you save this code, and try to run, so this is our first optimization. Okay, so earlier it was CPU code. Now we are trying to launch the we are trying to launch it using the CUDA kernel. So there is some mistake. Let me rectify it. Okay, instead of size they have used bytes. Okay, fine. That was a silly mistake. So we are compiling. Okay, CUDA malloc managed, spelling is wrong. She's saying I can tell what is wrong here. So I don't know what is wrong. Let me directly to the solution. Time we were directly discussing this. I'll share the solution so that I can. People, am I Am I audible? Hello? Am I audible?
Yes, sir.
Sorry, there was some network issue at my end. So, yeah, we'll compile this code. Just wait. Okay, there is some issue to fix. Okay, just wait. Am I audible? Am I audible? Hello? Am I audible?
Yes, sir.
Okay, fine. I'll I'll share this code in your chat. You can just have a look. You just have to remove these things while one apart. You can copy paste this code. Everyone copy paste this code in your notebook. just delete the first line. Okay. Remove the line number 108 also. So let me resend this modified code. This is the modified code. Just copy paste this code. Okay. You'll get two errors. Let us check what has happened. So line number 96 and line number 101. Line number 96. Okay. So line number 96, you put this. You just give the backspace. Make it line number 101. Okay. Now it should not give any errors. So it is compiled successfully. So let me share the again modified version. Everyone, am I audible? Am I audible? Okay. So just copy the code that I'm sharing right now and paste it in this file 01-nbody.cu that you get from here nbody. If you click on the nbody, you will see this, sorry, nbody.cu. You will see this notebook. You click, you control all and then that paste that code here, then save the code. Once that is done, you come back to the notebook. Okay, you execute this cell. Once this is done, you execute the profile command. Once that is done, okay,
Excuse me, sir.
yeah, hello.
Sir, I have trouble in Jupyter Notebook. Can you provide me any password or token for login?
There is no such password or token for login. You can directly log in to your
Yeah, sir.
account.
Just now I will do all the things, but before 10 minutes I did some suffering from that error, and I do all steps again and again, repeat from course and
No,
video.
you do one thing. You do one thing. You just stop the lab and then again relaunch the lab.
Uh, uh, if I stop the task, then it may be work or not.
What?
If I stop the task,
Yeah.
then it be work or not, or my work will
No,
be
no
waste.
problem. No problem. No problem.
Okay, sir. Thank you.
Yeah.
But sir, it shows your most recent grade will be saved, and my work is not done.
No, no. The progress won't be saved. Yeah, you will get everything again. Your progress won't be saved.
Okay.
Hello?
Yeah, sir. I do it again.
Yeah. Yeah. So is it done to everyone? Done with everyone? Hello?
From my
Have you
side,
compiled and hello? Is it done?
It is still giving
sir,
some
take
error.
some time, please.
Okay, okay, fine, fine. You do. Okay. I'll stop sharing my screen. If okay, Anjali, have you got any error? Okay, just wait. I'll share the modified code. Just wait. Just wait. Don't click on access button. Okay.
Sir, I put that code on last exercise now.